Hello everyone and welcome to another video for Elephant VFX Patreon feed. So this video today is going to be about creating these assets for your environment, which is basically some kind of snow pile or basically some kind of debris that is covered with snow. So let me explain a little bit more about that. So I have this reference folder here, and as you may know or may not, I live in Stockholm, Sweden, and of course winters are kind of harsh here. So I took these pictures the other day when I was walking my dog around the neighborhood where I live. And I basically looked into these kind of environment elements. Oops, this is not loading very well. This one is not, for whatever reason. Give it a couple of seconds maybe. Okay, never mind. That one doesn't seem to load properly. But anyway, so I was looking at all these environment pieces around the city. And as you can see here, this is basically, I mean, it depends on the reference picture, right? But generally speaking, what we're seeing here is some kind of debris. In this case, it seems like a broken asphalt and a little bit of soil and a little bit of pebbles and concrete. So, you know, just basically debris that you can find randomly around the city. And after a few days of snow, this pile of debris starts getting covered by the snow, and the snow also starts melting down and breaking up, and you get like these chunks around here, and then the snow on top also breaks up a little bit, and then some parts of this debris gets covered and a little bit of it gets revealed, and you can see the surface underneath. And it has a lot of nice patterns, right? Even here, you can see that these lines of breakup that generate these small details and medium frequency details that looks very nice. And depending on the picture, of course, it's going to be slightly different, but generally speaking, it's kind of like the same look overall, right? Like, again, like some kind of powdery snow on top, a little bit of breakup, these big chunks, small chunks, even smaller chunks here. And I don't know what's going on with this picture, so let's ignore it. And then this one here is kind of like the same thing. What I liked about this one is like you can see the powdery effect of the snow, but at the same time you can see different frequencies in detail, like all these small frequencies here, these high frequency details over here, and like the bigger chunks on this other side, and even bigger here. So it's quite complex in terms of detail, right? So yeah, I just took those pictures around the city, and I was wondering what would be the best way of doing something like this for an environment. And of course, there are a few ways that you could tackle something like this. If we're talking about, you know, a big environment where we need to see a lot of these elements, I would definitely use some kind of procedural work for that. So here you can see that this is probably like a curve or something, like a chunk of concrete that it has broken into pieces, and then the snow gets on top, and that's why you get these really nice breakups. So if you want to do something like this, I would do some kind of procedural modeling, and then some kind of procedural texturing and look depth to get the snow effect. And I'm pretty confident that I would be able to get something like this. I would have to rely a lot on displacement maps, and then the shader would have to be very nice in order to accommodate the properties of this material, the snow, you know, that so surface scattering and getting these bright colors without clamping the material. But I'm pretty confident we can do something like this. But I don't know, that's something that I've done in the past. I've done a lot of that type of work, not necessarily with the snow. Well, actually also with snow, but you know, I'm talking in general. That approach is a very common approach workflow to me. So I wondered, what if we actually do this with some kind of simulation, right? Because these are also like close-ups. So if I wanted to do something like this, I wouldn't do it with procedural modeling and procedural shading. I would actually do a simulation. So yeah, that's basically what I want to show you in this video, how we can approach some kind of snow pile with a simulation, but the goal is not to do a simulation. The goal is to have a static asset that we can place in an environment, but we're gonna benefit from doing a Vellum simulation to get the look, right? So basically, this is what I came up with. I did a couple of tests, I mean, just to see if this will work. Of course, this will need extra work and refinement and whatever, but at least, you know, I managed to get that look where I get some kind of debris, in this case, just a bunch of rocks, and those rocks get covered with this thick snow. So I'm basically getting this powdery snow look on the top, and then I'm starting to get those breakups that I liked from the references. Like you can see this breakup up here, a little bit more high frequency breakup here, bigger breakups, and then here we have like these big chunks and whatnot. And all of that kind of gets driven by the different settings in the simulation, so we can get different looks. I didn't want to spend a lot of time trying different things, but I thought this would be like a proof of concept. And this is the starting point to make some of these snow piles that you can find in cities. Right. So again, let me go back to my renders. This is actually like a work in progress for something else. This one doesn't look that nice, but you can see still, you know, all the breakup and the big chunks or the smaller chunks and the middle chunks and all of that. So, you know, it's good for that. This one, I think it looks a little bit better. But again, the goal is to get static asset, right? I'm not concerned too much about the simulation itself, right? I'm not really bothered about how the simulation looks and feels and the timing of the simulation and all of that, because I just want the final static asset to place in my environment. And the goal is, of course, to have a bunch of these assets with different resolutions based on distance from camera, and then just build your environment with these kind of assets, right? But I can show you the simulation. So basically, this is kind of like the simulation. So the good thing also about having a simulation is that you can freeze any frame of the simulation and export a new asset from there, right? So as you can see, I'm getting all these very nice chunks and breakups and all of that. And to get even more of those breakups, we can tweak the simulation, or we can also play with the collision geometry that we're using for this. But yeah, you can see that I'm getting something that looks quite nice, I think. Another thing to keep in mind is that if you want to reveal more of the surface that is underneath the snow, you need to play with thinner snow, right? Right now, I'm playing with something that is maybe 40 or 45 centimeters high, meaning that I get quite a lot of snow, right? So basically, by the end of the simulation, which is, somewhere around here, a lot of my debris is covered by the snow. That's because my starting point here, and actually you can see that I clipped my source geometry for the Vellum simulation, so you can actually see it here, right? Where my box that is emitting particles ends. And that's actually because I couldn't care less about the actual simulation. I only cared about the final frame. And then in order to speed up the simulation, to make it faster, I'm just using a small emitting source. That's where you actually see it in camera. Of course, if you are actually planning to render a simulation, you don't want to see this in camera. But again, just for iteration purposes, I didn't care too much about that. Why is this not playing now? Who knows? Let's play it again. But yeah, basically this source here is quite thick. That's why by the end of the simulation, everything is covered by snow. If you just want a little bit of snow, you would have to make it much thinner. But we're going to look into all of that now. So basically the goal of this video is how to set up a simulation like this to end up with something that mimics those references that we've seen at the beginning of the video. And again, this is based on powdery snow, like fresh snow. But at the same time, I want to create that, the clumping and all this small detail and all those things that we can see in the simulation. Okay, cool. Yeah, so basically I'm gonna show you how I managed to do this. It's a very simple simulation, really. I mean, this is just a grain simulation from Veloom. The only thing that is a little bit more tricky, I guess, is to create the clumping and create all the differences in detail, like all the different frequencies that we can find here. But the end result is very nice. And again, if you want to get different looks, you would have to play with the settings that I'm going to show you, and you would have to play with the source object, which in this case is as simple as a cube. And of course, with the collision geometry, that is basically the debris that you are seeing the snow falling into. Okay, so that's the plan. I don't know, I guess it will take a couple of hours to go through all of these. So let's jump into it in Houdini. Okay, so here in Houdini, first of all, we need a collider, right? We need a collision geometry because the snow is gonna fall into something. Based on the references that I showed you before, that's something we can build procedurally, or it's something that we can model by hand, or, we can use some kind of photogrammetry scan. That is up to you. But we need something to collide with the snow simulation. So in my case, I'm going to use Megascans. So I'm going to create a geometry here, and I'm going to call this one Collider. Okay, let me go inside, and here I should have, let me see if I remember where I placed these things. Here, I believe, yeah, I think this is the one. So I'm going to choose LOD 0, and this is huge. So let me just transform this a little bit. Okay, and this is basically my geometry, which is just a pile of debris. It's like this bunch of rocks. And what I liked about this is that we have this kind of gap in between. And of course, your simulation also is going to behave completely different based on the collider you're using, right? The more differences you have in vertical, the better it's going to look, because then there is space for the snow to collide and accumulate and go from here to there. This is not that big. I mean, this would be maybe, I don't know, a few centimeters, like 10 centimeters or 15 centimeters. So it's not going to make a big difference. But if we had something like a big hole here and then a surface down there, then it would look much cooler, of course. But yeah, I'm just trying to replicate something that I've seen in the streets. So I'm going to stick to something like this. If we wouldn't have anything vertical like here, I mean, here is not completely vertical because we have this kind of curvature here. But if this was completely flat, of course, your simulation would look quite boring, because basically everything would be falling on top of a flat surface. Imagine this is like a board of metal, for example, or wood. It wouldn't look nice at all. But here, because we have all these crevices and all of that, it will look hopefully a little bit more interesting. So again, let's take another look. So this is basically it. So yeah, you see that the snow basically is falling and is running around and is creating these very nice chunks of ice, and it looks cool, right? But again, in the areas where it's kind of flat, it looks boring, but that's how nature looks like, right? You have places where the snow is completely accumulated, so it's basically fully covered by snow, and other places where it's broken up, and then the vertical faces where you don't get much, and you find these gaps here and there. So just keep that in mind. Based on the collider that you use, things are gonna look different. Okay, so this scan, as you can see here, it looks nice. Of course, it's missing the displacement map, right? Because this looks quite low res, even though we're using the LOD0. So this is the high resolution provided by Megascans. It looks great once you add the displacement, but here it doesn't look that good. Is this good enough for a simulation? Probably, but it depends, right? If you're doing like a close-up, the render that I did is kind of something like this, so it's quite close. But if you're doing something even closer, of course, the simulation is going to collide with this geometry. And this geometry is not really representative of how the final thing is going to look like, because once you apply the displacement to this, you're going to get much more detail. So there are cases where you actually want to apply the displacement, bake that as a geometry, and use that high-res geometry as a collider, right? Instead of using this low-res geometry. Again, that it depends mostly on distance from camera. But in this case, let's pretend that we want to do a hero shot, and this is we're gonna get this close, and then we want to see all the details and have all of that available for the simulation. So I'm gonna show you how to do that. Well, here in SOPs, you should already know that, right? We've been doing that for years, and that is a very well-known workflow. I'll show it to you anyway, but I want to show you how to do it in Solaris also, because in Solaris, it might be a little bit, it is a bit different, but also it's kind of new, right? Because Solaris, even though it's been around for a few years already, still people are getting used to work with Solaris. So maybe you need to know how to do that, right? So I'm gonna show you how to do it. We're not really using it for anything today because the simulation is gonna happen in SOPs, but I thought it would be a good idea to show it to you how to do it in Solaris. So let's take a look. I'm gonna just add a null here. And this actually is gonna help me later because this is what we're gonna be using for rendering. So I'm gonna do something like collider render or collider low. That's probably better. Okay, cool. So let me save the scene, by the way. I'm gonna call this snow pile. Live English version 1, there you go. And I'm gonna jump into Solaris now. All right, cool. Yeah, so let's see how we can do this. It requires a couple of different steps. It's a little bit different to what we're used to do in SOPs. Right, so I'm gonna use a SOP import, and I'm going to import my collider low. So this is my geometry. I'm not gonna care about setting a structure here or anything because, again, this is just like a temp thing that I want to show you in order to be able to do this baking of the displacement into the geometry. Maybe we can call this collider low. All right, and I'm going to create a material. All right, and here we can just add a material. So I'm going to choose a Karma material builder. I'm going to call this one rock material. And now here we just need to connect the map. Let me choose the image. I think I'm gonna choose, this will work for anything that you want to bake into UV space, right? So the goal is to bake a texture into UV space, right? So then we can actually use it for displacing the geometry. In this case, it doesn't really make much more sense because we already have the displacement in UV space, right? I mean, this is an asset. This asset, let me go back here. This asset already has UVs, and this asset already has a displacement map in UV space. So we don't really need to do this with this. We're fine. We just need to apply the displacement in subs. That's all good, right? That's all good. But most of the time when you're working with environments, you're most likely building the surface or the ground or the terrain of that environment procedurally. Maybe you're building it with height fields, maybe you're doing it in another procedural way, but at the end of the day, you have something that is started from a procedural approach. And also the texturing and the look depth is probably going to be a procedural approach. You're going to be using most likely triplanars, right? And different masks and attributes and whatnot. So if you want to bake the displacement into UV space, you would have to do that because you wouldn't have a displacement in UV space already. So again, for this particular case, we don't need to do this step, but I just want to show you because most of the time in real productions, that's going to happen, right? You're going to have to bake everything into UV space in order to apply it in subs. So again, let's pretend that this is a procedural asset for now, and I can show you how to do this. So maybe let's choose the diffuse instead of the displacement, just because it's easier to see, right? It's easier to see albedo information rather than something else. So I'm gonna choose that, and I'm gonna connect it to the base color. Okay. And now I'm going to assign the material. So let me assign the collider and the rock material. There you go. And that's it, right? That is the actual diffuse texture. Again, I just don't want to use the displacement just because it's a little bit harder to see, but it would be exactly the same. I mean, you would get the displacement, or in this case, your whole procedural network and connect it to the base color, right? So if I select the displacement, we will get the displacement. Let's see if this updates. Yeah, sometimes it doesn't update. It's a little bit, let's see if by forcing a render, we actually can display it. Yeah, there you go. So now you can see that this is the displacement texture applied to the color, right? But again, I just want to use this still doesn't refresh. I mean, Solaris Viewport is a little bit funky sometimes, but I just want to use the color just to illustrate my point, but it would be exactly the same for any other texture channel that you want to bake. And again, this is just an image, but generally speaking, you would have a procedural network here. Okay, cool. So the material is assigned. That's all good. How can we bake this now into UV space, pretending that this is actually not in UV space, which it is at the moment? So let's create a camera. And this camera I'm going to call bake camera. Okay, cool. So now let's go to the clipping, and I'm going to set the clipping to a range that makes sense. Which is going to be from 0 to 2, and this will depend, of course, on the size of your asset. If you have a massive asset, you might have to increase the clipping, but try to keep it as low as possible. In my case, from 0 to 2 is just fine, right? Because I have less than 2 meters here. Then the aspect ratio. This camera is going to be used for rendering the image into UV space. So textures, generally speaking, are multiple of 2. So I'm going to set my aspect ratio to 1 and 1. Of course, if we look through the camera, it doesn't really make sense, right? but it is a square. That's all we need for now. Clipping and aspect ratio. Okay, great. In the material library, I'm going to create also, let me do it, see if can I do it here? No, I need to do it actually. I think I can do it here. I'm gonna create a karma. No, actually, sorry, I'm wrong. I need to do it outside. The Material X doesn't support this yet there. So I need to create a material network here. And in this material network, I should be able to create a Karma UV lens. Okay, so this is the shader that we're going to attach to the camera. Okay, so now back in my camera, if I go to Karma, I want to enable use lens shader, enable this lens shader VOP, and now I should be able to choose my Karma UV lens. Okay, cool. So now my camera is using this UV lens that basically is going to bake into UV space. That's it. I don't think we need to change anything in the actual shader. Okay. Let me create a render settings node. This one is going to take care of my rendering. Let me go here. We need to attach the correct camera. So I'm going to select my bake camera over here. And then we need to set the resolution. As you can see, it's already picking up the aspect ratio of 1 to 1. And here we can set this to whatever resolution we want. This would be the output of our texture, right? Again, I would usually go for 8K to 8K. For demonstration purposes and just to go as fast as possible, I'm going to keep it at 2K. So it takes very, very little to bake this information. It's going to take very little anyway because it's just one texture. But if we were using like a procedural network with a lot of nodes and a lot of operations and a lot of textures, it might take a while, right? It might take like up to an hour to bake everything into UV space. Okay. What else? Here in the Karma settings, the render engine needs to be CPU. As far as I know, baking into UV space using this Karma UV lens doesn't support XPU, right? So you need to stick to CPU, which is all fine. And somewhere at the bottom, we should have this texture baking option. Okay. So I'm going to enable UDIM. You can use UDIM or PTEX. We're going to use UDIM. The tile, I'm going to set here my naming convention for the tile. So I'm going to set it to 1001. We only have one tile here, but you know, if we had more, we could definitely bake the whole range. But you know, this is just one UV space, so we're good with that. The object ID, I'm going to set this one to 1. And I think that's everything here. Yep. Now in the default geometry settings, we should have something down here, which is texture baking. So we set the object ID to 1, right? Here in the global thing, in the texture baking, we set this one to 1. So make sure that here you're using exactly the same information. So where it says low resolution object ID, we set this one also to 1, so it matches the other one. And I believe that's everything we need to do. So if we add a USD render ROP down here, Yeah, current frame. This is static render. The only thing we need to do here is to actually output the image. So yeah, make sure you're using CPU. That's all good. And yeah, that's it. We don't have to do anything here. We just need to set the output image. So I'm going to render this as EXR, and I'm gonna render this maybe in job render bakes live English, and that should be it. So if we render this to disk, let me go to my scheduler. All right, so this is rendering here. So let me go to my Houdini render bakes live English. Should end up there when this is finished. It shouldn't take that long, right? We're rendering in 2K. The UV lens shader is a little bit expensive, so that's why it takes a while. But it should take only a few seconds. I don't think this will take that. There you go. It's done. So there you go. So now here we have our EXR. Let me open Nuke quickly. Okay, and let me take a look at this image. There you go. And I think we made a mistake, right? Because it doesn't look like an albedo, of course. My bad. So let me go back to my material. And what I want to do here is actually, instead of using the base color, I'm just going to use the emission, because the emission doesn't get affected by lighting, right? So I'm going to connect this one to the emission color. You can disable the base color if you wanted to. You can disable the specular. It doesn't really matter because it's only going to bake the emission. And now I'm going to go to the emission and set this one to 1, right? And the color is my texture. So now everything should work as expected. Let me render this again. And let's take a look when it's done. Okay, finished. We can close this. And now let's go back to Nuke. Let's take a look at this image. And there you go. It's still wrong, but that's probably a refresh issue. There you go. So as you can see now, the albedo has been baked into UV space and it looks fine. This is a 2K texture. It will take a little bit longer if you were using 8K and if you were baking like a big shader tree. So yeah, that's basically how you would do it. Just connect your displacement network to the base, to the emission color and bake it. And then it's already in UV space. And now you can actually use this to displace the geometry and have a better collider, more precise collider that it will interact better with your simulations. Okay, cool. So in this case, again, we didn't have to do this because we already have the displacement in UV space, but I just wanted to show you because again, most of the time you will be working with procedural geometry and with procedural shading and texturing, procedural look depth in general. The only important thing is like you need to have good UV mapping, right? So if this was something modeled procedurally, make sure you have good UVs with, no overlapping and no stretching, that kind of thing. And then that's it, you're good. Cool, that's everything we needed to do here in Solaris, at least for now. Let's go back to SOPs, because now we need to apply that displacement map, right? So let's go here, and in SOPs, I'm going to duplicate this, and I'm gonna call this one collider high. Okay, so we have low and we have high, and we can do some stuff here to make this look a little bit better. I'm going to hide the UVs. There you go. Okay, cool. And now we need to apply that displacement map that we baked, right? Or in our case, we didn't bake because we already have it. So the first thing, you need to subdivide the geometry, right? Because if you want to see the detail that's coming out of the displacement map, you need to subdivide the geometry. Basically what happens at render time, but you want to do it here live. So let's use a subdivide. Let's subdivide these, I don't know, like 3 times maybe. Okay, and this give us what? 1.4 millions. 4 times, maybe 4 times is just overkilling for an asset like this. Yeah, probably is. Let's see where this put us. There you go. So this is like 4.5 millions. All right, that maybe this is fine. So now we have enough geometry here in order to get the detail out of the displacement map. Okay. And of course, there are many ways of doing this. At this point, you can do it just with an attribute from map. You can do it with bobs. I mean, there are different ways of doing it. So use whatever you feel more comfortable with. The easiest way, not necessarily the best or the worst. I don't think it's better or worse than any other method, but the fastest, I think it is with an attribute from map. So yep, that's good. I'm gonna set this one to float, and I'm going to rely on UVs because this object has UVs. Okay. Yeah, and I'm going to select my displacement map, which again, this is something you would have baked before, or in this case, you just need to use the displacement in EXR format. Okay, this is all good. Let's pipe it here. And why is this complaining now? Oops, I removed the UV attribute by mistake, I think, right? Yep, there you go. So now we have UVs back and this is working. Okay, cool. So now let's displace it. And maybe I'm gonna jump a level because it's very hard to see. I mean, now you can see let me go to flat lighting. You can see the displacement is actually seen in the color because we're using an attribute from map, and this is outputting the attribute as CD, as color, right? But we don't want to do that. We actually want to displace the geometry. So let's go back to have a little bit of shading here, and I'm gonna pin the viewport here, just because if I go inside, I basically see the wireframe. So I'm going to pin the viewport here and now do these operations inside. Let's create an attribute bob. Okay, bobs are great. All right, and here I want to displace the normals, right? So, well, first of all, let's make sure that we have normals, right? Yeah, we have normals, then we should be good. Maybe, you know, displacing these 4 times is a little bit overkilling. I'm gonna go back to 3 because I can see it's a little bit slow. Let me pin this thing again, go inside, go to my attribute bob, and I'm gonna create a displacement along normals, which is going to displace whatever input along the normals of the object, and we already have normals here. Okay. Let's connect the position to the position. There you go. And we have a CD attribute already, right? Because we created it here. So we can use that. But first of all, we need to convert that CD attribute to float. So let me create a vector to float, and I'm going to pipe the color into the vector. All right, let's make a little bit of room here. Now we need to compensate for the 0 point of the displacement, right? Generally speaking, that would be 0, or it would be 0.5, depending on how the displacement was created. To be honest, and you probably realize this, Megascan assets are a little bit of a mess. Sometimes that's the case. They have a 0 non-displacement value. Sometimes they have a 0.5, but sometimes they have something in between. And even more, sometimes it's 0.6, sometimes it's 0.21, sometimes it's 0.18. It's a little bit of a mess. I think they've been getting better over the years, but they have so many assets, and some of them were created years before, I guess before they have some kind of standardization in the company. So it's a little bit of a mess. So you need to guess. So let's pretend that is 0 or 0.5, right? And I believe for this one is 0.5. I don't remember. But we need to compensate for that, for the non-displacement point or 0 point or midpoint or whatever you want to call it. To do that, we can use add subtract constant. There you go. So we only care about the red channel of the displacement, right? Because it's a grayscale map. So let's connect the red channel here. And here is where we compensate for that. Make sure this one is a uniform float. And I'm going to set this one to 0.5. So it's basically going to subtract 0.5 from 1. And that will give us the midpoint, right? The value where it shouldn't do any displacement. Okay, right. I'm going to connect this one to the amount of the displacement. Cool. Now I want to get rid of the color of the displacement. So to do that, I can just do like a constant and set this one to, let's say, 1 and connect that one to the color. So now this is just white or 0.5, whatever you want to use. Let's use 0.65, something like that. Okay, cool. And now here we can change the scale of the displacement, right? So maybe we have to tweak that a little bit. All right, so let's connect the displacement to there. Okay, and I'm gonna set this one to 1.5 maybe, so we get a little bit more. This is not working, as you can see. And the reason being is that we started with these normals, but after displacing it, we are affecting the normals. So we need to create new normals afterwards. This is something that we don't do when we apply the the displacement at render time. We don't do it as users, but the render engine does that automatically for us. Because we're doing it here in the geometry, we need to recreate the normals. So here we need to recreate the normals. There you go. And now we have it. Okay, so now we have this displacement. But it's definitely an issue with the bounding box or with the midpoint. And this is what I was saying here, right? So let me go back to 1 here. Oops, sorry. I didn't want to do that. I wanted to do this. So yeah, basically this is the issue, that I think this is not really working. So if we set this one to 0, we can see it's not working. 0.5, it's still not working. So just increase this a little bit. And that's what I was saying, like the Megascan's assets are a little bit of a mess. So basically we just need to check between this and that. There you go. And now it seems quite good, I think. Yeah, I don't know if we can tweak this a little bit more. Maybe 0.8. Yeah, that looks very nice to me, right? So we don't have bounding issues. There you go. So now this looks much better, right? Because we're going from something like this, where everything is blobby and there is no much detail, to something like that, where, you know, we have all the nice detail of the scans. If we want to get a little bit better detail when it comes to high frequency detail, we would have to increase the subdivisions. But for a collision geometry, that's really not important, right? What we care about is like the bigger chunks. And here we're getting all that detail. that we were missing before, right? These will look much worse when we simulate than this. Okay, so I think this is everything that we need here. Let me tighten this up a little bit. Okay, and now we have our low resolution collider, which we're not going to be using for as a collider in the simulation. We will use this only for rendering, because at render time we want to render the low resolution with the displacement map applied to it, and then this one will be used for the simulation. Okay, I don't know if you want to change the color to white, maybe, so we have the same colors here. All right, cool. So now we're good and we can move forward. These might take a little bit to calculate. So what you can do here, you can maybe add a stash, right? And then you can say stash input, and now it's calculated. So that's all good. It won't take any time to calculate. The issue with this is like when you open Houdini, it will take a while because it needs to go through all the stash nodes that you have, and you know that might take a little while. So instead, let me delete that. All right, so instead, maybe you just want to cache this out, right? So you use file cache here. There you go. Let's say this is not a simulation. Let's say this is a single frame. It is not time dependent. And let's put this one in job, geo, and maybe call this one live English or something like that. And we want to call this one collider high, something like that. Save to disk, and now this is cached to disk, so it will be as fast as possible. Okay, cool. And I don't know, give it a black color to keep things identified. There you go. We're good. Fantastic. Okay, great. Are we done with the collider? I don't think so. We probably want to add a little bit of extra ground here, right? That can be whatever you want. Let's just build something very quickly, procedurally, and that should be fine. I'm going to do this. Let's put a merge here. Let's create a grid. There you go. So now we have a grid. We have to make this grid bigger, I guess. Where is that grid? Yeah, that's quite small. So make it maybe like that. Needs to be bigger, right? I mean, whatever you want to encompass in your camera, right? Let's see, I don't know, make it a little bit bigger, 100 by 100. There you go. Now this covers everything. Let's add more subdivisions here. Let's take a look at that. Okay, we can unpin this guy. There you go. And maybe add a little bit of noise. Mountain, there you go. All right, and let's make these much bigger. Not too much. I mean, not. We don't want to make it extremely noisy. Oh, what about that? I don't know. Let's take a look. Is it too irregular? No, I think it's fine. All right, that's all good. Maybe. Okay, let's continue here. Now we need to make an emission, right? An emission geometry. This is the collider. Now we need to emit particles from somewhere. So let's jump out and let's create another geometry. And let's call these source. Let's call these grains source. Okay, let's go inside. Now, what do you want to use as a source? Well, it depends on the effect that you want to create, right? Again, in my case, I don't care too much about the simulation. I only care about the last frame or, you know, a frame in the middle, something that I can use later as a single frame to create a prop or a natural element for my environment. So a box will do, right? How big should this box be? Well, it should be as small as possible because you want to simulate as little as possible, right? The bigger the emitter geometry, the bigger the simulation would be. And you don't want that because, you know, when the simulation is bigger, it will take more time. And to iterate, it will take more time. So it will get you there much slower. So make it as small as possible. So I'm going to make it of a size that kind of encompass the whole asset. So let's make these 20, maybe 20, 30, maybe 30. Okay, cool. And and then we want to make this also as thin as possible, right? Because let's say we emit particles from this whole cube. I mean, this is 30 meters, right? I mean, we're not really working at scale here, but this is 30 units. So this is 30 meters of snow. We don't want that, right? We want something smaller. So I would go to something, and to be clear, maybe I can do it like this, 30, 30 and 4. And this is probably too much. Actually, this might be too small. Let's make it 50 by 50. There you go. And maybe like 1. All right, cool. This should be enough. Yeah, because otherwise, I think it was too small before. Because of course we want to get, let's move it up. Actually, let's don't do it here. Let's do it here. Okay, a little bit up. So I'm gonna make this as close as possible to my thing. So something like that. If I put this higher, the only thing that's gonna happen is like snow is gonna come down more violent, right? It's gonna come super hard due to gravity and due to the mass of the actual snow. So maybe that's something that you want because most likely that will create bigger breakups in the snow, right? Due to the forces applied to the simulation. If you put it that close, it's gonna come down more gentle. So I don't know, 6.5, something like that. And then this is the thickness of the snow, right? So if you want to get less snow, again, if we take another look at my render, by the end of the simulation, we have a lot of snow. That is because the snow is quite thick. If you want to make it less snowy, if you want to get more breakups, not breakups in the sense of these chunks, but in the sense of revealing more of the underneath surface, you want to make this box thinner, right? So I'm going to keep it like this. I think this is very similar to what I use in my example, but if you put here 0.1, then you will get way less snow, right? So that depends on the effect that you want to do. I'm going to put it like that. Okay, that should be it. Let's actually create a camera. Let me hide this for a second. And I'm gonna go, I don't know, that's up to you. I'm gonna do something like this, perhaps. I think this is something similar to what I did, right? Let me take another look. Yeah, I think I'm even closer in my thing. I don't know. Yeah, let's do something like that. Let's create a camera. There you go. Let's put the camera over here. Render camera. And I'm gonna set this one to full HD or whatever resolution you wanna render. There you go. Okay, maybe a little bit farther away, so we have a little bit more breathing room. All right, let's pretend that is good. Okay, back to the grains source. So as you can see now, my grain source is covering everything. We can see a little bit here in the frame. Again, if that bothers you because you actually want to use this simulation, just make the box bigger so it's off screen, right? You don't want to see the trick. You don't want to see the source here. Again, in my video, in my render, you can see it right here and here. That's because I couldn't care less. I just care about this, having this as a static thing, that a static prop or environment asset that I can use for building an environment. But if you actually care about the simulation, make sure that your box is bigger than or is out of the framing of your camera, right? Because otherwise we're revealing the trick. But keep in mind that you will need more particles to have the same resolution as my simulation. And my simulation is not extremely high resolution, but it's quite high res. So yeah, the bigger the source is, the longer the simulation will take. And we can actually optimize this even a little bit better because we can use the frustum of the camera to break this, right? Because we have a lot of this box that is off camera, outside of the framing of the camera. So let's optimize that a little bit better. Okay, cool. But for now, this box will do. Now, let's add a Vellum configure grain. There you go. Nothing really happens yet, right? That's because we need to enable create points from volume. We do that. There you go. And now we have particles here. And as you can see, these are not that many particles. I mean, if you take a look at these, each of these would be like a grain of snow, right? So if you count 1, 2, 3, 4, 5, 6, 7, I don't know, we have like 15 or something here. And of course, this is volumetric, meaning that, inside there are spheres. So there are in total, you can see here, like 3.4, almost like 3.5 million points. That's not good enough for a simulation. So we would have to high-res this up a little bit more. So here we have the particle size. So of course, if you set this one to 0.05, this will take a little bit more time to compute, but at some point we should see it. There you go. So now we have way more spheres. So if we take a look here, now we have 27 millions. All right. So be very careful here because, this is not exponential. This is not an exponential value. We went from 3.5 million to 27.6 million by changing this from 0.1 to 0.05. So be very careful with that. Okay. We don't want to do that just yet, right? We want to work as fast as possible while we're building the setup. So I'm going to set the particle size to something like 0.2, which is a very low res simulation, but this is just like, not even 500,000 points. So that works for me. Okay. What else can we do here? Maybe because we're going to be jumping to that setting, jumping into here quite a lot. Maybe let's expose that parameter here. So maybe let's do a edit parameter interface. I'm going to make those invisible. Just create a folder here quickly. Simple. I'm going to call this one Elephant VFX. Elephant VFX, and let me create a float, and I'm gonna call this one resolution. Okay, and I'm gonna set it to 0.2, and let's link those parameters. I'm gonna copy parameters, go here and paste relative references. There you go. So now, because this one can be potentially quite heavy, we're gonna build something big here. So, it's quite easy to just come here now and change the resolution here. Very simple. Okay, So I said 0.2, right? So let's set that to 0.2. Okay, we're good. Now, let's actually remove particles based on my camera frustum, because, yeah, let's see. We have like 358,000. So let's create a camera frustum to get rid of that. Camera frustum. I think I showed you before in another video how to create a camera frustum. Houdini doesn't have a tool out of the box to create a camera frustum to delete stuff based on the frustum of the camera. There is nothing out of the box as far as I know. I know of 3 different ways of creating a camera frustum. In that video that I'm mentioning, I think it's one of the mixes. You know, I have those mix videos where I show you maybe 3 or 4 different topics in one video that are not related between them. And I think in one of those about particles, I show you how to create a camera frustum. So I'm going to show you now a different way of creating a camera frustum. And I know another different way of creating a camera frustum. So yeah, I know 3 different ways of creating camera frustum. There are probably other ways, but these are the 3 that I know. So yeah, because I already showed you one, let's show you how to do it in a different way now, which is very similar, really, but just a different approach. But the end result would be exactly the same. So let me do this. If you create a BDB, right, you can say here, voxel size, frustum, and from camera. So I'm going to select my render camera. There you go. Let me display this. And let's see if I see something. There you go. Here is my my thingy, right? My BDB. Okay. So you have the near and the far. So let's say set the far to 50. And as you can see, this is basically creating a frustum, right? Do we need to go farther away? I think so. 70. Okay, let's do something like that, and then we can take a look through the actual camera. But yeah, basically this is what we want to do. I think we don't care too much about the, you know, the starting point, but we can manipulate it here. Okay. Let's create a UV texture after the balloon grains. There you go. And in the texture type, I'm going to select perspective from camera, and let me select the render camera itself. Let me look through the camera. And what I want to do is basically project or create a UV attribute based on the projection of the camera. Attribute class, I'm going to set this one to points because we're working with particles. And now let's create a point wrangler. And here we can actually use those UV coordinates. I mean, the only thing we did this here, the UV texture, is to create a UV attribute that is based on the camera projection, right? So now we can access to this, and remember that I have a video about Bex. So we're going to be typing Bex here. I'm not going to explain too much, but basically I just want to delete based on the UV space. What I mean by that is that right now we don't see it. We can visualize that a little bit better with an attribute color. Let's do that in a minute. But basically what we're doing here is projecting UVs or a texture, in this case a checkerboard, based on the camera. So we can invoke those properties, right? So if we create an integer here and we call it something like delete x, and we say this is equal to a vector attribute because we are calling or invoking the UV attribute, so that is a vector. So we say a vector attribute based on the UVs in the x direction, and we want this to be less than 0. Or the same thing, vector at UV attribute dot x bigger than 1. Okay. If we do this, can we visualize this somehow? I guess if I do at CD is equal to an integer value called delete x, right? There you go. We should be able to visualize this, right? And I call this del x. There you go. Let me do this first. Let me do integer at delete. I'm gonna do it like that. Is equal to del x. And maybe we can do just like that, right? What did... There you go. Okay. Yep, that's working, right? Yeah, that is working. Cool. Right. So to recap, what we're doing is we're creating this attribute, right, that represents the frustum of the camera. And what we're saying here is, let me create an integer attribute called delete x, and this is equal to the UV attribute when it's less than 0 or when it's more than 1. So when we look at the camera, less than 0, because we're starting from the left, less than 0 is what is here. More than 1 is what is there. Right? So we're creating this mask. Okay, cool. Let's do the same for let me copy this. And let's do the same for the y-axis. So I'm gonna say y is equal to vector at UV in y less than 0, and same here, more than 1. So now it's going to do the same in the vertical axis. So well, we need to add this to this attribute. So the delete attribute is going to be equal to delete on x or delete on y. There you go. And now this is our camera frustum. So when we take a look through the camera, we can see that outside of the frustum is white and inside is black. So essentially we just created a mask based on the frustum, of the camera. This might be too tight. I think for our simulation is probably fine because we don't care about the simulation. We only care about the end result. But generally speaking, you want to give it a little bit of margin. So you want to have a gap or like you want to extend the bounding box. You don't want to get stuck in a very restrictive way to the frustum of the camera. You want to expand that a little bit. So we can do that by this. So we can add a property here basically. Well, I mean, we can multiply this or add a margin, or we can just create a small controller here. So if we do minus channel, let's create a channel for that, and let's call this x margin, something like that, right? And let me copy this, and here we do the same, but here it would have to be positive, right? And let's call this one y margin. Okay, that should do. And we should be able to copy this and paste it here. There you go. And same here. I'm gonna copy that. And again, if you're not very familiar with PEX, just take a look at my video. I have another video coming probably next month about PEX. So yeah, that's it. Now let's create those parameters, and now we can, there you go, we can play with this value, so we can expand it a little bit, right? So let's expand this by 0.1, 0.1. This is probably too big for my taste. I don't know. No, might be fine. All right, I don't want to expand it too much, right? So maybe something like this is fine. Yeah, there you go. That's, I think this is too much. Yeah, I mean, we're wasting all this thing. So maybe 0.05, 0.05. All right, that gives us a little bit of margin outside of the frustum. That's good enough for this case. If you actually want to see the whole simulation, you probably want to expand that a little bit more, okay? But basically, yeah, this should be good enough. All right, we don't need this VDB. This, I just wanted to show you how this works. So basically, you just create a frustum. All right, so now we actually need to get rid of this. So we're going to be saving quite a lot of particles, right? Because all of this is outside of the camera, we don't really see it. So we will save quite a lot. Okay, so yeah, let's get rid of those particles. By the way, this black color, I don't want to see it. This is just to visualize the mask. So we can comment this perhaps. There you go, and now it's gone. And now we can just add a blast. And in this blast, because here we created this del attribute, we can just say run over points, and we can do here at del equals 1. There you go. And now we are deleting based on that attribute. So basically we went from 358,000 points to 171. That's great, right? Because at some point we're gonna get this thing and do something like 0.05. So now we have here, we had 27 million points, and when we blast the frustum of the camera, we get like 13 million. So we're saving quite a lot of things here. Let me go back to 0.2 for now, because I want to move as fast as possible. Okay, I think that's everything we need for the source, right? I mean, it's quite boring, it's quite flat, it's quite thick, so we're gonna get this very well covered by snow, but this should be good enough. All right, let me add a null, and I'm going to call this. All right, so let's create, no, actually we can just create a top network here. This would be the simulation, so I'm gonna call this grains sim. Okay, great. Let's go inside. We have our output. Otherwise, this is completely empty. We need a Vellum object. Okay, and in this Vellum object, let's hide this thing and let's hide that thing for now so we don't see anything. Let's display the grid. So our Vellum object, we need to select the initial geometry. So the initial geometry is going to be the grain source that we just made. So let's go to grains source and select the out. There you go. And this is the source. Great. Display geometry, we can display it or we can just hide that. That is up to you if you want to display it from here or if you want to display it from there. Okay, I think I'm going to keep it here. So I'm basically going to set this one to hide the geometry or not display the geometry. Let's keep it for now. What else do we need here? We need, of course, the brain of all of this, which is the Vellum source. And we also need some initial forces. So let's create gravity. Okay. So as you can see here in the Velum source, we are required to connect an object to solve, particle forces, and post-solve. So this is the object that we want to solve. And this is the gravity. And we connect that one to the output. So this should be the skeleton of the simulation. Let's play this and see if it's actually working. Okay, so let's press play. There you go. And as you can see, this is quite fast. It is working, right? Of course, we don't have any collision yet, which is fine. And we don't have any extra forces or any other thing. But this is working, and as you can see, it's quite fast. Grains are actually quite fast. But of course, once you start increasing the complexity of the simulation, it will take a little bit longer. What else do we need here? We need the collider geometry, right? The collision geometry. So to do that, we are going to use static object. Let's visualize this and let's select it. So if we go to the collider, we have the collider high-res. Let's select it and look at that. But don't be fooled by what you're seeing here, because this is not the real collider, right? This is the geometry that we prepare to become a collider, but this is not the actual collider. If we go here to the display geometry, we can hide it. And now if we go to collision and enable collision guide, why don't we see it? No. I think we don't see it because the uniform subdivisions is very low, but this is actually what I wanted to show you. So right now it's not seeing anything as a collider, but if we increase this to maybe 60, there you go. This is what Velum considers a collider, right? So not this super high-res geometry that we have here, but this. So of course we need to increase these subdivisions. And this is going to take a while. Like if we set this one to 150, there you go. So you're getting a little bit better collision now, but this is not near enough what we need. So let's increase this quite a lot. We can actually make our own collider using BDBs, whatever, but this is what Velum is doing internally. So, you know, you'd rather do it automatically or you do it manually. It doesn't really matter. You can choose either way. I'm just going to set this one to maybe 600. And because we have a very high resolution geometry, this is going to take a while to compute. As you can see, my thing is spinning. So this might take a few minutes to compute. So I'm going to pause the video here and we will continue in a few minutes. Okay, this is done. It actually took only like a minute and a half or something. And this is what Velum is seeing as a collider. You might want to increase this even a little bit more. So I'm going to go to 800. And this will definitely take more than a minute and a half. This will take maybe like 5 minutes or so. So again, I'm going to pause the video again and we can continue in a few minutes. Okay, so this is my collision geometry. I'm happy with it. So I'm going to disable collision guide. I don't want to see this. And I'm going to merge this into my simulation. So let's create a merge here. Let's pipe the gravity there and make sure that your merge, the relationship is set to, the affector relationship is set to mutual. So both of them come into the simulation in no particular order. Both of them are kind of working at the same time. We might want to go here and show the collider and look through the camera. I'm gonna save the scene quickly. And now we should be able to run the simulation. So I'm gonna set my timeline to, I don't know, 70 frames or something like that, at least to start with. And I'm going to do, I'm going to do a new flipbook. I'm going to set the size to full HD and start the flipbook. So let's see how long it takes. It shouldn't take too long. But anyway, I'm going to pause the video here and we can continue in a second. Okay, so this only took a few seconds. So let's see it together. So that's how it looks. It looks terrible at this point, of course. Maybe we can see this from the viewport. It shouldn't take that long, I think. There you go. And something you can see here is that the particles are jumping around like crazy. Right? That is insane. I mean, it's doing what it's supposed to be doing, right? We are getting the proper collisions and everything. So this is fine as a starting point, and it's colliding well with the ground and all of that. We don't see any intersections, but they are jumping like crazy. Yeah, I mean, that's crazy. And the reason being is that in the Vellum solver, you want to go to sub steps and increase this to 10. This is going to make everything more stable. It's going to take longer to simulate, but it's going to make everything more stable. So let's cache this out again. Maybe we can just cache it from here so we can play it in real time. And this hopefully will prevent everything to jump around as crazy as before. Let me pause the video here. Okay, this took a little bit longer, but just a couple of minutes, really, 2.5 minutes, I think. So let's take a look now. There you go. So this is much better, right? So now things are not jumping around like crazy. Of course, it doesn't look any good yet because, well, this is just the basics of the simulation. We get some gravity, we get some collision, we got some very low res particles. We have like 170,000 particles or something, so we need to go up to millions to make this look good. But at least things are working, right? So this is the very basics. So that's great. So what is next? Now we need to work with clamping. We need to build some kind of clamping system that creates chunks that stick together to each other. And then we also need to add constraints. So things break based on whatever we decide to use as a constraint network. And that would be really it. And then we just need to create the high resolution thing. But yeah, we still have a lot of work to do here, but this is working, right? This is working. And yeah, this looks very nice to me. Okay, cool. So let's close this thing and let's carry on working on the simulation. All right, let's continue with clamping. Clamping is going to make these chunks stick together with each other. Well, that would be actually a combination of clamping and constraints, but let's start with clamping. So basically, instead of all the particles falling at the same time, or actually falling at the same time is another issue that we're going to have to tackle later. So some particles start falling before others. But basically, with clamping, what we're going to achieve is creating clamps, creating groups of particles that stick together to each other. So let's see how we can do that. So go back to the simulation, right? And if we select the Vellum solver, which again is kind of like the brain of the simulation, we haven't done anything at all here, right? The only thing we've done is to increase the substeps from 1 to 10. And that prevents particles to bounce around and go into, you know, crazy places when they hit a collider. So that's good. We don't need to do much there. For everything that is done with grains, I generally go from 5 to 10 substeps, and generally speaking 10. I never had to increase this much. I never done like super crazy grain simulations. So maybe or potentially you might have to increase this a little bit more. But for everything that I've done so far, I always use 10. There is another video that I'm working on related to grains that hopefully is going to be quite cool. And that one is definitely way more violent. Like there is like a lot of particles flying around, and I'm also using 10 sub-steps. So hopefully 10 would be enough for most of your grains work. Okay, so in the Vellum solver, if we go to the Advanced tab, here we have grain collisions. And here we have an attribute called attraction weight. So this parameter, let's see what it says there. I'm waiting for how much the particles will naturally stick together when close. A value of 0 will disable particle clamping. Okay, so that is already a hint. If this parameter is set to 0, we are not going to get any clamping. And at the moment, we're not getting any clamping. So we're going to take this attraction weight and we're going to set it all the way up to 1, meaning that all the particles will stick together. Let's cache this very quickly and see what we get. Okay, so let's take a look at how it looks. There you go. So now everything is clamped together, which is cool because we're already, when the tension it's too high, it's breaking. So it's creating these chunks that they are going to look like frozen snow or chunks of ice, which is what we want to get. The problem is that the attraction weight that we changed to 1, it's the same in the whole area, right? And of course, we want to introduce variation. So some parts are actually clamped together and some parts are not clamped at all. Right now, everything is clamped together. But at least we know that the attraction weight is working as expected. Okay, great. So yeah, let's break it up a little bit. Let me look through the camera and let's see if we can play this. Yep, you can play that and you can see it, right? Like that's looking very cool. I mean, this kind of breakup is what we want to get. But again, we want to break it up a little bit. So I'm going to go to my grains source. And yeah, we want to control this with some attributes. So let's make a little bit of room here. So let's add a point bob. So now we can manipulate the particle look with some noises and some other elements here. All right, so let's make a little bit of room. Let's add anti-alias noise, or any noise really can work for this. Let me connect this to the position and let me connect this to the color so we actually see how this looks. Okay, cool. So if we pass this information as an attribute for the attraction weight, we're going to get clamping where the noise is white, and we're not going to get clamping at all when the noise is black, right? So this is basically what we want to do. But let's make it a little bit more complex. Let's make bigger clamps, perhaps. Yeah, something like that. Let me take a look at the thing. We can play with this offset a little bit if you want to. Basically, what I don't want is this, which is basically a harsh cut between the clamp and the non-clamping area. So maybe 0 was actually fine, right? Yeah, because now everything is kind of broken up in a nice way. So that looks pretty good to me. Right, so that will create these big clamps, and all of these will fall together, and when the tension is too high, it will break, right? So that's pretty good. Let's fit these a little bit better, so we make sure that we have 0 to 1. So let's add a fit range here. And maybe we can do something like that, so it's very clear what is clamped and what is not. There you go. Just give it a little bit of variation, so we have still a little bit of gray scale in between in between the weight, the 0 weight and the 1 weight. If you push it too much, it will be like the whole thing and it won't look that good. So maybe something like 0.4, 0.25, I don't know, something like that. Okay, cool. That looks good. Right, so this will be the first level of clamping. I'm going to duplicate these and this, let me connect this one there. And let's make this like a higher frequency. Maybe we can go all the way to 1. Yeah, that looks probably good. What about 0.8 perhaps? Let me compare both. Yeah, let's go maybe a little bit higher. Something like this. Okay. And now I'm gonna set the source max to something a little bit different. So we had 0.3, so maybe something like that. So it's a little bit harsher, just to give it a little bit of variation, meaning that this will stick together even more than this, which I guess makes sense because these ones are smaller, right? Okay, cool. Let's combine these two with a maximum. Let's combine that one, and connect that one there. And now we have these two working together. Okay, great. We don't need to see this in the color anymore. So let's create a bind export. And let's export this as attraction weight. Attraction weight. Make sure the spell is correct. Attraction weight. That's fine. Okay, great. We can visualize that here if you want to. I mean, we don't have to, but maybe for caching purposes, it makes a little bit of sense. At least when we are doing like flipbooks, so we can see it a little bit better. So we can just create a color here. And let's set this one to points, and let's use ramp from attribute, and let's choose the attribute attraction weight. There you go. So here we can see it. Maybe we can change this to something a little bit better, like I don't know, something like that, right? Or whatever suits you better. Actually, I'm gonna do grayscale and I'm gonna set my own colors. So let's set this one to red. Let's set that one to, or actually, let's set this one to green. Let's set that one to red, and let's do something in between that is blue. There you go. And maybe make this constant. So it's very easy. And actually, I think it's better as linear. Right. So now we can see the different zones of clamping, right? Okay. Yeah, let's play it and see how it looks. Let me save this and just do another flipbook. Okay, let's take a look. Cool. Now we can see the attribute in action, right? So basically all the green particles don't have any attraction weight, so they move around like a powdery snow. And then we have the blue and then the red sticking together much more, creating those nice clamps, right? I think another issue that we have is probably the friction by looking at this playblast or this simulation. And if you look closely, you can see that the particles are kind of moving quite a lot. So these are quite heavy particles, or they are supposed to be quite heavy, and you know, it's a lot of snow here. So I think they should not move around that much. They are sliding too much now. It depends on the effect that you want to create, right? But in my case, I think I'm going to make them a little bit more less bouncy, or basically I want to add friction, which currently we don't really have much. So if you go to the static object, there is this physical tab here, right? So we have this bounce that I'm going to set to 0, and the friction that I'm going to increase to something like 10. Okay, let me cache the sim again and see what's the difference. Okay, let's take another look here. Yeah, there you go. And this looks much better now. So now particles are sliding a little bit, as they should, but not like crazy as before. But again, this is in terms of how do you want it to look, right? Depending on the effect that you want to do. Okay, that's good. That's good. We're getting there. What are we missing here? But we're missing some constraints, right? So we force some bigger chunks to actually stick together so they break when they fall. And we also need to change the activation time, because at the moment all of them are falling at the same time. So there is no that many options for the clamps to break. They only break when they collide with the geometry. So let's make them fall at different times. But let's start with the constraints. Let me save this. So I'm going to go back to my grain source, and this one we can call attraction weight. Okay, so we know how it's called. Let's put this over here. And let me add another point bob, and let's create some kind of constraint network here. Let me call this constraints. Okay, cool. So let's add another noise. Maybe we can use a borrow noise now. Connect this one to the position. Okay, and let me connect the C to a bind export, because we need this later. So let's call this one class, and this should be an integer attribute. This is what is required by the constraint network in Vellum. Okay. So let's add maybe a random here, because we want to visualize this in the color. So let's connect that one to the color. This one should be one float input and a 3D output, right? Yeah, because the color is a vector. Let's connect this one here. That's what we get, right? So basically, what we're trying to create here is these ice chunks, right? If you take a look at the render, we're trying to create these chunks of ice, you know, that they are more like icy snow or yeah, basically like frozen snow that is not that powdery. Let's perhaps add another borrow noise. Let's create a couple of different frequencies. These, what did we use here? Here we use 1, 1, 1. So maybe let's use something like 1.5. Okay. And let's put this over here. And I'm going to add these both two together. There you go. Okay, that should be fine. Let's see how this one looks like. That one looks like that. That one looks like that. Yeah, that should be fine. Before, when we mix noise, we use a max, right? So this will give you a different result, as you can see there. So it's up to you. It's basically just play with something until you get, of course you need to do a couple of test simulations to see how it looks. But yeah, let's try with add this time. I'm gonna keep the max here just in case that I don't like it, so we can switch it for the max. But basically, yeah, we will create like a slightly different looks. But it's chaotic, which is kind of what I want. So that should be fine. Okay, so we're exporting this as the class integer attribute that is required by the constraint network. So that should be good. Okay. We're still visualizing the attraction weight attribute, right? So we can disable this and we will see the constraint attribute there, or the constraint mask there. Okay. We need to mask this out though, because again, the same thing, right? We are getting this constraint network in the whole piece, right? In the whole emission source. We don't want to do that. We want to mask it out a little bit. And by the way, something you need to keep in common, something you need to keep in mind is that once we increase the particle resolution, because remember right now we're working with a resolution of 0.02, and for the final resolution we're going to work with something from 0.05 to 0.03, something like that, maybe 0.05 to make it not that slow. This will look slightly different, right? Because we would have more resolution, so these chunks would be more defined, right? So that's something you need to keep in the back of your mind. Actually, let me show you. If we take this one to 0.05, it will take a little while to calculate. Let's keep it running for a few seconds. There you go. Look at this. This looks completely different, right? So that's something you need to keep in mind. Keep playing with noises and all of that, but once in a while, check with your simulation final resolution, because it can change how things look like. But yeah, let's keep it to 0.2 for now. Okay, that's good. Let me save. Let's mask it out. So let's make a little bit more room here. Let me create an attribute wrangler. Okay, make sure this one is running over points, and let's create a threshold for that. So I'm gonna say if, and let me create like a random function here. The attribute that we created here, it was called class, right? So let's invoke that one here. So if random, we need the integer attribute class, it's bigger than whatever we define here. So let's create a threshold of some kind. Okay. If the class attribute is bigger than the threshold that we need to set here, let's create an integer attribute that we can call keep is equal to 1. Okay. So let's do that. And now let's start playing with this. So let's give it something like, I don't know, 0.8 or something like that. And now let's see the output of that. So we can see that with a blast or with just a split, right? So let's, how do we call this? Keep, right? So if we say here, run over points, and we say the attribute keep is equal to 1, there you go. This is what we get, right? So let me add a null here, another null here. So this is what we're keeping. This is what we are deleting, right? So now with this threshold, we can keep more or less. So these are basically the constraints that we are going to create at the end of the day. So we started from this, very uniform. Everything will be constrained together. And now we can do more or less. I think 0.8 was probably fine. Okay, great. So all these would actually take care of the constraints. Okay, great. But the constraint networks, we still need to create that. So let's do a connect adjacent pieces. Let's put that one there. All right. And this one is actually complaining. That's because we need to set it to adjacent points. There you go. Now it's working. The search radius, this one needs to be set to, this is basically the p scale, right? So let's set it to something that encompasses everything. So let's take a look here. Yeah, so something like 0.2, right? Seems right. It's kind of getting all the pieces. Oops, sorry, 2. Or almost all of them, which is fine. So basically, these would be ice chunks, right? Meaning that all these points encompassed, between these wires will stick together. They will move as a chunk. This, by the way, will make your simulation go much slower, but it will look much better, right? It will look much more complex and chaotic. So it's definitely worth it, even if it takes more time. Okay, cool. Great. Another thing to consider here is like now we're using a max search points of 100, which is fine for these, but once we increase the resolution of the particles, because we're gonna have way more very close to each other, this would be overkilling. So let's reduce these quite a lot, maybe not that, maybe something like 6. That should be fine. It won't look nice with these. But again, think about the final resolution, right? Because between each of these blocks, we would have a lot of particles, where right now we only have like, 2, not even 2 inside of one of these. So now it won't look that nice, but later on it will look very good. Okay, just keep in mind the final resolution. All right, we need to export also this length attribute. This is necessary for the Vellum constraint network. So make sure this one is being exported, and you should see it here as a rest length attribute. It's a primitive attribute. Constraints usually work with primitives. Okay, there is one issue though, and it's this. You can see that all of these are kind of connected in between. Or not all of them, but most of them, right? That's why we get these kind of gray lines. So we need to get rid of that. And the only way that I know of getting rid of that is by actually using a little bit of Bex. So let's add a primitive wrangler, because again, constraints work with primitives, and let's type a little bit of code here. So we need to create this attribute. Let's call it point 0, and this would be the prim point. There you go, prim point, and that would be 0, meaning the first point. And then we use the variable or the global attribute prim number. And that would be the first input. All right, let's copy that, paste it there, and then we do the same for point 1, prim point, and that would be from 0 to prim number 1. There you go. Great, let's export this with an integer class equals to the point, and same thing, it will be 0, and then we need the attribute class that we created before, set to the point 0, there you go. Let's duplicate that, and now let's go to point 1. Okay, and now we need to say, so basically here we're setting, let me see what I did here. Okay, that's all good. Let me see what I made here. No, we're good, right? Yeah, I think we're good. So basically what we are declaring here is what is the starting point of the constraint and what is the final point of the constraint, right? We're defining that here based on the prim point and the prim number. And we are then exporting this as a class attribute that is required by the constraint, right? So what we can do now is if class 0 isn't it the same as class 1, then we need to remove the point, right? So those things are not together anymore. Remove prim, and then we say input 0 at prim number 0. There you go. Class 0, where did I make the typo? Class 1, remove prim. Oh, sorry, my bad. There you go. Okay, so let's see if that's actually working. Yeah, it is working, right? So you can see that this chunk was being connected to this other chunk by these lines here. And now we are basically saying with these lines of specs, we're saying where this one ends and this one starts, we want to remove the thing in between. So as you can see now, it's not there anymore. And you can see it in many places, right? So basically we're not creating these big chunks, we're creating this one. And whatever is connecting them in between, we don't do that, right? Because otherwise they all will stick together. I mean, not the whole thing, but a lot of them will stick together. So by doing this, we are removing a lot of those connections. So we get even like more variations. Okay. All right. So let's pipe this one here. Okay. Right. Actually, where am I? Constraint, there you go. Yeah, sorry. I didn't want to do that because we want this, but we also want the rest, which is that, right? So let's connect them together. So let's create a merge here. Let's put that one here, that one there. Let's get rid of that. Move this kind of like over here. And there you go. So now we have everything together here. Right. What else do we need? Well, we actually need the constraint and network, right? So let's create a Velum constraint network. Let's pipe it here. Okay, let me add a null here, and there you go. This will show us the constraints. So let's call this one out constraints. We're going to have to use this later in the simulation. So let's have it here as a null. Here we can actually see the wireframes of those constraints. We can get rid of that. well, there are a couple of ways of doing it, but we can add an add node here, and we can click on delete geometry but keep the points. There you go, and that should basically remove those wireframe constraints. Okay. Okay, cool. What else do we want to do to the constraints? Let me think. I think we have pretty much everything that we need. Yeah, I think that's pretty much it. The only thing we need, I think, is just to play with the activation, right? So let me take a look at how everything looks like. So I'm gonna look through the camera, and to make this test, I think I better increase this a little bit more, like 0.1. I don't want to go all the way to 0.05 to make it fast. There you go. So I'm gonna keep it like this, and I'm gonna do a play blast, or sorry, I'm used to the word play blast, but a flipbook. Okay, so I'm gonna stop the video until it's done. All right, let's take a look at the sim. And let's see how this looks. Maybe now it's a little bit distracting to see the attribute weight, but doesn't really matter that much. Okay, cool. Right. So yeah, the constraints are working very well, and the chunks that we made before are working very well. So the combination of both make things quite nice. Yeah, I think this is all good. Okay, cool. All right, so I think the only thing that we're missing at this point, and look at these, like these chunks kind of moving together and sliding on top of the rock, looks very nice, right? Yeah, definitely. Look at how this bounces, and then you get like the powder on top of the chunk and all of that. So that's basically what we want. And this is going to look much better once we have the final resolution. Okay, I'm happy with it. So the next step is to work on the activation. We want these to happen not at the same time. Right now, everything is falling at the same time. So we want to break that up a little bit. So basically, and I think a good way of doing it would be to split. Let me pause that. Oops, I didn't mean to do that, sorry. Maybe we can split this thing in half, right? Like we have this gap in the rock, which is very nice because, you know, this kind of divides, this gap here, this kind of divides the two highest points of the surface, which is this rock and this rock, right? So we can make like a line here, and then we can kind of start start filling this gap with this cube. So imagine that we have a line here, and we start the particles start falling from this direction and then from that direction and gradually to the sides. That will things make a little bit better, which is what I have here, right? That's exactly what I've done here. So, you know, things are kind of falling gradually, starting from the middle point. That's up to you. You can design that in the way that you want, but I designed it in that way, right? So we're starting with this kind of zigzag type of shape here, so we get these these breakups. So let me hide this for a second, go back to the grain source, and here let me add a primitive wrangler, and make sure this is primitive, right? Because when we deal with constraints, we are working with wranglers. So make sure you're using primitive wranglers and not point wranglers as before, right? One thing is the actual particles, the grains, and another thing is the actual constraints. So we need to pass this information to the grain solver. So basically, we need to create a stitch property or attribute, and that would be string. So let's create a string attribute type, and this is equal to stitch. Okay, Then we need also a string attribute that is called break type. And these are properties of the actual solver, right? And this should be called stretch stress. Okay, and then we need some kind of break threshold. Break threshold, and this is gonna be equal to whatever the threshold you want to break this thing, right? So I'm gonna set this one to 0.001, something like that. Okay, where did I make a mistake here? Well, here, right? Okay, there you go. So now we have this that is going to be used by the solver. Okay. So basically what we're doing here is breaking those constraints, right? Because they were a little bit all breaking at the same time. So now they are going to break based on this break threshold. All right, so that's constraints. What about activation now? We don't want everything to fall at once, right? So let's create some kind of growth system, which is what I showed you in the render. So something that starts something around this point and starts opening to the sides. But again, that's the design that you want to do. So let me do one thing. I'm gonna create a grid here. Let me display this thing on. Okay, let me make this a little bit bigger. Something like that. And I'm gonna set this one to XY because I want to, let me look through the camera. I'm gonna try to do kind of the same thing that I did, right, with my render. So yeah, I wanna use this gap here as the midpoint for this. So let me take this guy and rotate it. So it's kind of like there, right? Kind of right in the middle. All right. You can do whatever you want, but this will work for me. Let me perhaps add more subdivisions and let me add a mountain. And I want this to be very low frequency. So let me increase this quite a lot and make this quite big. Something like that, even more. No, maybe not that much. 15 and 5. Maybe what I had before was just good enough. Something like this. Maybe we want a little bit more subdivisions here. Well, let's do something like this. So, you know, we get like these big gaps here and protrusions on the other side and whatnot. Maybe we need some kind of normals here, right? To make this a little bit smoother. All right, let's pretend this is good. Okay. Let's add an attribute wrangler here. And let's create an active attribute here. So, oh, my language is wrong. There you go. So let's say that this is active equal to 1. All right. Cool. Let me go here. We need to put that before we mess with the attraction of weight. Let's add another wrangler, and here it would be the opposite. Here we can say active equals to 0. So nothing is active here and everything is active here. So now we can transfer that attribute and activate based on that geometry, right? That's a very common workflow for you know, many things in Houdini. So let's create an attribute transfer and transfer from here to there. Maybe we can put this here. There you go. Let me make some room. Let's visualize that attribute. So I'm gonna create a color. I'm gonna set this one to ramp from attribute, and let's call this one active. There you go. And maybe, yeah, let's keep it like that for now. So yeah, as you can see, we're transferring from here to there, and we're visualizing the attribute here. Of course, this is too big, and the reason being is that when we go to conditions, here we can control that, right? So this is that grid. So it's going to, this is basically what we want to do. We want to start here and expanding this thing. So we need to animate this, and everything will fall when it becomes white, right? That is basically what we want to do. All right, so maybe we can change colors here if you wanted to. So maybe set that one to blue and maybe set that one to red. That's a very common color coding for activation. That's what effects people usually do. So let's mimic that. We only need to transfer to make this a little bit faster. We don't need to transfer anything on the primitives, and we only need to transfer the active thing here, the active attribute. So that's all good. And yeah, let's make this, I don't know, 0.5, 0.2, 0.3, something like that. So this will be the starting point. Yeah, I mean, this, let's see how it looks through the camera. Yeah, I mean, that looks cool, right? It looks like, I mean, I don't know, it's up to you. You can always go back to the mountain and start changing this a little bit more. I don't know. I think it was fine before, right? This, no, I don't like this. It looks a little bit too straight here. All right, let's perhaps do, let's see if we get something that we like from the camera. Ooh, that looks cool. That is quite big. I'm wondering how this is gonna look. I don't think I make this that big in mine. But let's experiment with that, or maybe we need a little bit more frequency. Sorry, let me go here. All right, something like that, maybe. I don't know. This looks now too. There you go. That looks cool. Because then we have these big frequencies and then smaller. That looks cool to me. Back to the attribute transfer. So make sure that we encompass the whole thing. Now we have some breakups there, which is not bad necessarily. Actually, we're going to create even more breakups. But yeah, something like these. Yeah, that should be fine. Okay, great. I'm gonna go to my simulation. This is not updating, right? I mean, I guess if we play, it's gonna update. Oh, by the way, let me go back. How can we make this a little bit faster? I'm going to disable simulations here. So in this little brain, right, if we click here, now we're disabling simulations, meaning that if we press play, we don't see the simulation, because we want to animate these, but we want to animate these on a static particle sim, because it would be very hard to animate these while the particles are falling down. And also it would be very time consuming, right? Because now we have a lot of particles and it takes a while to simulate. So we want to do the animation first and then we want to simulate it. So let me go here to the simulation. I'm going to get rid of these. Well, not get rid of it. I'm just going to move it over there for now. And I'm going to create a multi-solver. So we can add multiple simulations inside of the same simulation, or inside of the same DOP network. So let's connect that one there. And now let's do a sub solver and connect this one to the second input. And well, on this one here. And something that I want to do is I want to disable these in order to simulate only this sub solver. So that's very easy to do here, right? In DOPS, the only thing that you need is enable solver, right? Is it called enable or disable? Enable, yeah. So you can connect this one here and disable the solvers. So now if you enable the simulation again, let's see why this is complaining. I guess it's not, you just need to recalculate the thing, I guess. Okay. Why is this complaining? Let me reset simulation. What have I done wrong here? Oh, sorry, my bad. So I'm going to connect the Velum object to the first input of the multi-solver and the Velum solver to the second input. There you go. My bad, sorry. And now the sub solver is going to be connected also there, right? So now we have both at the same time, but this one is disabled. Okay, that's how it should be wired up. Okay, now things are good. So if we press play, it's simulating, but the heavy part, which is the Velum solver, is being deactivated here. So now we can just focus on this other sub solver here. Okay. Cool. Back to the grains source. Back to the grains source. We need to, where is the attraction weight? Here, right? So this is basically the attraction weight. So we probably want to move these before we are doing all this operation. So let's make a little bit of room here. All right. So I'm gonna cut them from here and I'm gonna paste them before I do this whole operation. Like that. Yeah, that's better because I wanted to do the activation after I have the attraction weight thing and the constraints. That would make things much faster. I think it could work the other way around, but it just will take more time. Okay. And also, well, right now, we should be looking at the active thing, right? Yeah, there you go. So now the last thing that we see is this active attribute here represented in blue and red, where blue basically is not activated, meaning that it's not going to be simulated, and red is going to be simulated. Okay, back here, and now we should see that here once this refreshes, right? There you go. Now we refresh this by resetting the simulation, and this is what we see in here. Cool. So the sub solver, right? This is where this is going to take care of this animation, the growing of this active attribute. but we need to animate that because at the moment it's not really being animated, right? So if I press play, this is not growing. So we need to make the growth system, which should be quite simple. Right. So let's go inside of the subsolver. There you go. And here we can take care of that. So let's do that. So here we need to do basically kind of the same operation that we did in the grains source, which is transferring all of these, right? Transferring the activate attribute. So let's do that. Again, we're here, we're inside of the subsolvers, and here we have all the inputs. Let's put this down here. This is fairly simple, actually. So I'm gonna add an attribute transfer, same thing as we did before. And I'm gonna connect the DOP geometry to both inputs here, right? So let's do something like that. And the group here, the source group, let's use the source group that we had before, which is the active attribute, right? So let's say the source group to active equals to 1, okay? And the destination group is going to be active equals, oops, not to 9, but to 0. And both set to points, of course. There you go. Cool. And now, well, let's go to conditions and play with this. Let's set the distance threshold to something like, I don't know, 1 to start with. Okay, that should look good, I think. All right. So now if we press play, there you go, we should see this animation growing, right? Yep, that's all good. So it is working. I guess the issue here is that, well, first it's going too fast. And second is growing too uniformly. So we can add a little bit of breakup here if we wanted to. I mean, if we keep only these, our simulation will look much, much better than before. So we don't really need to do extra steps here if we don't want to, especially because we only care about the last frame, right? But if you actually cared about the simulation, most likely you would have to add a little bit of breakup here. So why not? Let's do it, even if it takes a little bit more time. So maybe, well, to control the speed, we can do it in multiple ways. But because we had this grain source, we have this global control here. Let's edit this parameter interface and add a control for the speed. So I'm going to add another float parameter, and I'm going to call these something like speed. And I'm thinking that we're going to mix two different noises or two different speeds. So maybe we need to create a couple of different parameters here. So let's do speed slow. Yeah, I think this will work. So let's do that. So we have this speed slow now. Let's set it to 1. And let's copy parameters here. Let's go back here. And let's paste it here. Paste relative references. Okay. So now we're controlling these. Let's reset this guy. There you go. So this now is being controlled by these parameters. So if we set that one to 2, reset this guy, now we'll go faster, right? And if we set this one to, let's say 0.2, it will move slowly, right? Which looks a little bit better. All right, let's keep it to 1 for now, and we might adjust that a little bit later. Okay. We have an issue that we're not seeing yet, and is that right now we're seeing the color out of here, right? This color attribute here. But once we start manipulating these a bit more, we're not really gonna see it. That color is not gonna work. So we need to replicate that color here. So just add a color again, and we'll do the same, right? So let's set it to points. Okay, that's good. Let's choose again ramp from attribute. We need to use the active, and let's set this to the same thing we had before, which I believe it was blue and red, right? Okay, so this will update properly now because it's actually been simulated, that color here. Otherwise, we wouldn't see it growing later. Okay, that's good. Right, so I don't know if we want to adjust this already or a little bit later. Let's do something very slow. Like that, okay. Well, we need to tweak this parameter, right? To get something that you like, that's up to you. But the issue that we still have is that it's very uniform, right? So we still need to break it up. That's what we were meant to do before. So let's do it. Let's maybe, I'm thinking, yeah, let's add an attribute wrangler here because, well, we are creating this animated mask, but this is not hooked up to the simulation yet, right? So basically we need to hook it up. So we have the attribute, the global attribute active in the simulation. So we need to pass this information. What we can say here is we can use the global attribute stopped, and we can say this is equal to when it's not active, right? Meaning that, well, if it's not active, it would be stopped, basically. That's basically what we want to do here. Why is this complaining about? Oh, right, because this is a, right. So basically we have this attribute here. It's a float, and this is expecting an attribute. So basically it's going to round this up. So instead of, being instead of being 0.125, it's going to round out to 0.1, but that's fine. It's not a big deal. I mean, if we change this one to, let's say, that, this one shouldn't be complaining. Oh yeah, sorry. Yeah, I mean, we would have to use integer attributes, but that's fine. I mean, not really gonna matter that much. So let's set this one to 0. Okay, let's do that. All right, not a biggie. Okay, we're good. Yeah, so let's add a little bit more complexity to the growth system. So I'm going to duplicate the attribute transfer here at the top. And I'm gonna connect this one to the second attribute transfer. So now we are creating two different growth systems here. For now, let me just disable this to see what this is doing. And at the moment, it should be doing exactly the same because we haven't changed anything at all. Right? So let's create a point bob so we can add some noises and play with them inside. So I'm going to connect it here. And I'm gonna connect it to the second input of the attribute transfer. So let's go inside. Okay, so let's read the active attribute. So let me create an bind here, and let's point to active. Okay, let me create a noise. I mean, use whatever noise you want to use. And what we want to do here, we want to use the time as a factor, not only the position, right? So let me add a vector to vector 4. Let me connect the position to the vector. And now we need the time. The time should be connected here. So now we have fourth dimension, right? So we have X, Y, and Z that corresponds to the position. And then the fourth vector would be the time. We talked about this in the Vex introduction course as well. All right. So I'm going to connect this to the position of this noise. Okay. And let's multiply the active attribute by this noise. Okay. Can we see this here? Oops. Can we see this here? Yes, we can. Okay, that's good. Or we can just bind export it, right, as active. And we should be able to see this, maybe not just yet, right? This one should be updating. It's not updating. All right, never mind. Okay, well, just for now, let's connect this one there so we can actually see it. Okay. Cool. So we went from this, which is very uniform, to that is a little bit more broken up. And this is exactly what we wanted to do. We still need to play with time, but in terms of breaking, this looks cool. We can probably make it a little bit more evident, so we get like more defined chunks here. So what we can do is, in the noise, we can play a little bit with the amplitude. There you go. I think we can go even more crazy. Something like that. Okay, that looks pretty decent to me. We might also want to make sure that this is not breaking anything. We can probably clamp it, right? So we make sure that we go from 0 to 1 and we don't break anything just in case. And this should be an integer value. So let's do a float to integer. There you go. And I mean, to be honest, I think this will work. But just in case, you know, we break something, it doesn't like something, because the actual, the active attribute goes from 0 to 1, right? Remember when we did, when we went here to the Vellum solver, and this, I mean, active is 0 to 1, right? It is active or it is not active. So yeah, we shouldn't have, we shouldn't have anything above 1. I think Houdini is smart enough to know that. So if you connect this here, even if this is over 1, hopefully it will clamp it automatically, but just in case, just do this and that should fix it. Just in case, but I'm not sure, to be honest. Give it a go if you want to. Okay. What else can we do here? So here we have the frequency, right? So we can increase this to make it more broken up or less. I think I want to have it less because it's too much at the moment. So maybe half of that. All right, let's do something like that. So we get like bigger chunks, meaning that, you know, this will start before, and this will start later as soon as it starts growing. Okay, right. So that's it. Let me do one thing here in the grains source. Let me perhaps here, I'm going to add an attribute delete and delete the color so we don't see anything at all. Let's see if that works better. If we reset these, there you go. So now you can see the growing. Yeah, this looks pretty cool, I think. It looks more organic and more broken up, right? Okay, that's good. But I think we have an issue, and the issue that we have is like we're getting these islands, right? And that is that is because I still have this one that I haven't activated yet. That's why. So we have these growing, but then this one should catch up, right? Yeah, there you go. But now we need to change the timing between both of them. So we get all the broken up areas that we created with the noise, and then that one should move faster. And then, so this one here should move faster, and this one here should move slower to cover. Yeah, so we get these, right? And then we get these islands that we don't want to get because this would be a piece floating in the air. So we want this to start, and then this one to catch up a little bit slower to cover those islands. That's basically what I want to achieve. There. Okay, so we did this speed slow. So let's edit parameter interface again. Let's add another float and maybe call this one speed fast. All right, something like that. I'm going to copy this parameter. All right. So I don't know, let's use something like 0.1 for slow and 0.2 for fast. So they, the fastest attribute transfer moves twice as fast as the slowest. So let's paste that thing here, right? So delete and paste relative reference. So here we have 0.2 and here we should have 0.1. Okay, that is correct. All right, let's take a look, see if things are working. There you go. So now we have the broken pieces, and then the other attribute transfer is filling the gaps quite fast. All right, that's good. Maybe we can slow this a little bit more. Yeah, I mean, that also works, right? Well, no, here is creating those pieces, so it needs to move faster. What about 0.3 perhaps? Yeah, that works very well. And again, keep in mind that once we increase the resolution of the particles, this will look probably slightly different, but most likely it will look better. All right, I like it. Great. What else? Well, let's go here and let's enable this guy that we have disabled before. So, okay, we need to do that. We need to reset the simulation. And I'm going to cache this and see how it looks. Okay, so let me just cache this. It will, oh, wait a minute. It's actually not working. Why is not working? Something is complaining here. Sometimes you need to, oh, this one is complaining. Why? No, that's good. Why is this complaining? Connection input 0 is the wrong type. What do you mean? That's bonkers. I mean, there is some kind of weird thing here. It's probably a refreshing error or something. This shouldn't be complaining at all. It's complaining about this guy, but why? Okay, let's reconnect that and connect it again. Huh, that's weird, right? Yeah, that's weird. I think I mean, everything seems good to me. I don't think we did anything wrong. Yeah, this is all good. Yeah, I mean, that should all be working. All right, let me restart Houdini and see if that fixes it. Yeah, sorry, I just realized that I made this connection here by mistake. That shouldn't be there. Okay, that was a mistake. I connected that. I don't know why. Okay. So yeah, we can keep this guy here if we wanted to, that we had before, in case we want to do more tests. Make sure that for now it's just enabled. All right, that should do it. Okay, so I'm gonna cache this simulation and let's take a look when it's done. So let's cache this. It will take a little while. So I'll come back in a few minutes. I had to stop the caching because I realized that I made a mistake. All my particles were kind of jumping around, and that was because in this second attribute transfer, I had forgotten to enable the points active attribute that I wanted to transfer, right? So this was like that, and then it was messing up with my simulation. So I caught it when it was like 10 frames or something. So I just activated this again. I mean, I transferred the attribute transfer and points, and now it should be fine. So I did a quick test and it seemed to work. So let me go back to 0.1. I just did 0.2 to test if it was working, and it seems to be working now. So again, I'm gonna cache the simulation and see how it looks. Let's see you in a minute. Okay, this is cached. So let's take a look. Cool. So it's working, right? It's working very well. Now things are not collapsing at the same time. We're getting this gradual growing here, and as you can see, we are seeing the chunks and all of that forming, some stuff breaking due to the tension, and things are looking good. And this is going to look much better later when we do the high-res simulation, right? So I think that's the only thing we need to do here. I mean, we can tweak everything we've done, but generally speaking, this looks quite good. Maybe the only thing that we should have done is to expand a little bit the collider, or just use less of the camera cooling to get a little bit extra, because here, as you can see, we're getting like not enough stuff, but that's fine. I mean, it's not a big deal. We're gonna have some kind of ground there, right? This is the grid that we have in the background. We can add some kind of snow material, whatever. But yeah, this is looking quite good. And of course, we need to simulate more frames, right? Because right now I'm only simulating 70. So we need to simulate something around 150 to 200 to get the whole thing, because this is not going through everything. But I didn't want to wait that long. But things are working fine. right? So now it's up to you to kind of tweak this simulation. Great. So that's all looking good. So the only thing we need to do now is we need to cache the high-res simulation, right? So how can we do that? So let's take the grain source and set it to the final resolution. The final resolution that I use in my render is 0.05. We could go for this. I mean, this is a close-up, so I would suggest to go to maybe 0.025. That will give you much better resolution. Let's take a look again at my render. Right, so in my render, you can see that some of the stuff is not super high res. It doesn't bother me too much here when we go to the final frame. It looks fine, but you know, if you feel like this is very granular and you want to get something finer, you need to increase the resolution. I think for this is fine because, you know, this is kind of fresh snow, so it's fine that it looks a little bit noisy. But if you want to get something a little bit better, just increase the resolution there. Okay, but yep, I think we need to reset that. Okay, so this is what we get. Cool. So how many points we have here? 13 million points. Okay. We're going to do a little trick here to make this even higher res without simulating more. But yeah, 13 million points is what we are going to cache for the final simulation. So let me do one thing. So here we have this thing, that's all good. So let me create another file node here. And I'm going to call this something like grains out, and this is going to be the container for the simulation. Let's go inside, let's get rid of this, and let's create a dope.io. Okay, and this, as you can see, it also creates automatically the file cache for you. So in the dope import field, we need to select our grain simulation. Let's display that. And the default object, it's going to be the Vellum object, right? So this should give us basically the oh, by the way, let me delete that for a second. As you can see, you don't see anything at all. That's because we don't have any fields imported here. So we just need to click plus, and this will hopefully bring everything here. There you go. Yeah, then you don't even have to select this thing here. By default, it's looking at the geometry. So if you type here geometry, that's basically what it's doing, right? It's importing the geometry. But if you typed here something different like hello, it wouldn't know what it's looking for. So by default, it's looking for the geometry. So you either type geometry here or you don't type anything, and it will import the geometry automatically for you. Okay. Yeah, that should be it, really. That should be it. But yeah, here you can select the Vellum object as well, but otherwise I think it does it automatically. And if you don't know how this is called, just do something like Vellum. You know that it's something Vellum related. So if you just type ** Vellum, it should look for it automatically for you, right? But otherwise just select it here, and that would be the same thing. Okay, what else do we need here? So in the compression tab, we need attributes to delete. You see that there is a lot of attributes here. So by default, it's not deleting anything, but we don't need all these attributes, right? And there is nothing wrong with keeping all these attributes, but it's going to make your files on the disk much bigger. So what I would suggest is to delete all the attributes, but only keep what you need. And we only need p-scale, and we also need velocity, right, to get motion blur. There you go. So now everything is gone, and the only thing we see are the points, right? We don't see the spheres anymore. The spheres, by the way, what you see here, these spheres, these are not geometry, these are sprites. So this is a texture, right? This is a texture. That's why when we deleted all the attributes, we don't see that texture anymore, because that texture would be, I guess, a material or something. We should have a texture, right? This texture here. So because we're deleting that, we don't see the sphere anymore, but we don't want to see it. We just want to cache these points. So now in your file cache, you can call this one whatever. Snow sim. Make sure you're rendering, well, whatever. I guess we need to change this to maybe 150. Okay, so 1 to 150, we want to render the frame range. This is a simulation, this is time dependent. Give it a folder where you want to export that. Could be like job, geo, sim, something like that. All right, and now that's everything you need. So click on save to disk, and this is going to take a while. I think on my computer, this took, I think, 4 hours. Or no, a little bit less, like 3.5 or 3. Okay, so this is cached. I'm not gonna pretend that I waited 4 hours for it. I just opened one of the old caches that I have. So it might be slightly different, but overall it would be the same. And if we take a look here, I just did a flipbook, and yeah, seems like everything is working, but obviously you don't see much here. This is just millions of points doing its thing. So yeah, I mean, it's hard to see what it's doing, but it's doing what it's supposed to be doing. All right. Okay, cool. So let me save these. So I'm gonna save this as version 2. There you go. Right. So Snow, it's basically, it behaves like a volume. So we need to convert this into a volume. So let me go to one of these frames, maybe 72. Okay, that looks fine. You know, it's like, or maybe even earlier. Or even earlier. All right, something like that. Let's look through the camera. I'm gonna go to my grains out. This is the cache. So because we are converting this into a volume, first of all, we need a density attribute, right? So let's create a density attribute. So let's create an attribute Wrangler. It's running over points. That's good. So let's say density is equal to 1. So now we have a density attribute there. Okay, now we can add a volume rasterize attributes. There you go. And nothing really happens here. And that's due to attributes. So let's set that one to density. There you go. And now we have a volume based on the density attribute. That's all good. That's all good. We need to change a couple of things. First of all, the voxel size. So the voxel size should match your particle size, which is 0.05. So we can just copy that parameter and paste it here, paste relative references. So now we have the same resolution, 0.05. That's all good. And then we have this coverage scale, which is a multiplier. Well, it's not exactly a multiplier, but it kind of behaves like a multiplier of the density. So let's increase this quite a lot. There you go. And now this looks a little bit more like Snow, right? So let's, I mean, it's still hard to see without rendering, but this is, yeah, I mean, you can see it here, right? This is how it behaves. So that's pretty good in general, I think. And it's quite fast, as you can see. All right, cool. So I'm happy with this. Oh, by the way, in this volume rasterizer, make sure that you check velocity blur, otherwise you wouldn't have appropriate motion blur. Okay, let's add a null and call this one out. Okay, this will do for now. But, and this is going to be rendered basically. We have an issue though. I mean, we have right now, well, actually this is packed at the moment. So we might have to unpack this thing. Let me take a look here. So we can do the operation before, of course. So let me make some room here. So right now we have like 10.5 million points, which is not really enough for this thing to look nice. And as you can see, we have a little bit of step in there, and that's because we don't have enough resolution. So there is really nothing you can do to fix that. You would have to make a simulation with high resolution, but I'm not too worried about that. Actually, this might even look cool, like clamps or something, but we need more points here. We need way more points here to make this look nice at render time. Because as you can see, this is quite sparse. So you have two options here. You increase the particle resolution like quite a lot, like 0.025 or even 0.01, and that will give you like a really nice looking resolution, really nice looking simulation, because it will be super high res. Or we can cheat it a little bit, right? So the way to cheat it a little bit, it will mean that we're going to add extra points after the simulation. So instead of, because it took like 4 hours to do this simulation, if we increase the resolution a lot, it will take 15 hours. If you don't want to do that, and for these environment props, I don't think we need to do that, we can add more points after the simulation. And that's what I want to do now. So I'm going to add a point replicate. And this is very common. You would see FX artists doing this all the time. I've definitely seen this in many shots in the past. So I'm going to add a point replicate. I don't want to add that many points. Let's do something like 10 points. So what this is going to do, this is going to take every point and add 10 more points around it based on a radius, okay? So let's connect this one here. Let's activate it. Let's see if Houdini doesn't crash. There you go. So now we added 10 more points per point. So here we should have now 105 million points, because of course here we had 10.5 million points. So this looks much high res now. That's good. But now we still need to calculate the radius, the p scale, right, of each of those points, because basically, what we want to do, we want to encompass all these extra points around the same radius. So if this point has a radius of, let's say, 1, we want to place these points also in the same area, right? How can we do that? So here in the shape tab, the first thing that we need to do is to set the type to a sphere, right? Because we're rendering these points as spheres. So it makes sense to change that from box, from a cube to a sphere. And this uniform scale, we're gonna set that one to 2.5, right? Because we're using a p scale of 0.05. So we need to expand that. Now we're adding 10 extra points, so we need to expand the uniform scale to something around 2.5 or something like that. So we're expanding each point. If we're adding, if a single point was 0 before, was a as 0.5. Now we're expanding it, so we're going to expanding it to something like 2.5. And we need to go to attributes, and we need to copy all the attributes that we had before. So the new points basically inherit the same attributes that we had in the simulation. Okay. Now we need an attribute wrangler here running over points. And what we need to do is basically attach all those points to the original p-scale, right? So we changed the p-scale here to 2.5 to encompass everything, but now we need to make it part of the original 0.05 p-scale. So we can say something like p-scale should be the square root, right? Because we are working here in square roots now, because we are adding, I mean, basically the radius. We need to calculate the radius, and the radius is basically calculated in square roots. So that would be CV RT. That's how you establish square roots in Bex. And we need a channel that is going to be called something like number of points. Okay. Click there. And this number of points should be whatever p-scale we were using before. So that's 0.05 multiplied by 0.5, right? Because we need the radius, and the radius will be the half of the p-scale. Okay, so let's do that, and that will give us 0.025. Great. I think that's pretty much it. So let's connect this here. Let's display all of these. Okay, let's see. Actually, let me do one thing here. Let me delete that, because that shouldn't be like that, should it? So here we have how many points? We have 10 points, right? So in this one, actually, we want to use those points, right? Exactly, yeah. Because now we want, sorry, that was my mistake. We want to calculate the square root or based on the number of points. There you go. And what we want to do now is here in the volume rasterized attributes, we have a voxel size of 0.05, right? But because we're adding a sphere around it and we want to calculate, we need the half of the radius, this is where we want to do this. So here we should do multiply by 0.25. There you go. And this should give us a way smaller voxel resolution. There you go. And this hopefully should give us what we want. Let's take a look. There you go. All right. Yeah. So now this is way more, we have way more resolution here. So again, we have like this amount of voxels. Okay. That's good. Okay. Yeah, that should be good. All right. So from here, the only thing we need to do is render this. So you can cache this if you want, right? You can just add a file cache here and cache everything up. This should not take that long. Well, actually it does. I mean, it's not as bad as you would think, given how many points we're using here. Right? Okay, but yeah, I'm gonna cache these. So let's add a file cache, and let's cache this, and we'll come back in a second. Okay, so this has been cached. It took a little while, but now everything is here. Now, of course, it doesn't play in real time, but you know, it plays quite fast, so we can move to any particular frame at any given time, and you know, we can do test rendering with any frame that we want to. Yeah, that looks pretty cool, right? Okay, cool, great. So this is it. So the rendering side should be fairly simple now because this is a volume, so we just need to use some kind of volume shader, and now it would be all about playing with lighting and materials and all of that. But I want to keep it very simple because this was mostly, you know, about how to create the asset itself. So let's go to Solaris and do like a base quick render. I'm not gonna spend a lot of time there. We'll give you the basics and then you can carry on yourself. So let's go to Solaris. There you go. We have the texture baking thing that I placed here before. So now let's do a SOP import, right? Or actually, you know, we need to organize this a little bit better. So let me go here. So we need this collision geometry, and that would be the out collision, right? Actually, no, not that, but this, right? The low version and the ground. We need these things. And then we need, what else do we need? And then we just need the grains out, right? That's it. So yeah, let's go to stage again, and let's fish for the out low. Okay, so let's call this one like rock or debris or whatever. So this would be the rock, then this would be the ground. So let's go here, let's pick the ground. Great. Let's merge these. We also need the grains, right? So let's call this one grains. And let's find the grains. So that would be grains out. There you go. Great. Let's do camera import. So we can import our render camera. What happened there? Something happened there. Oh, of course, it's importing this automatically, sorry. Let's look at the camera, and this is what we get. All right, just to set the lighting quickly, I'm going to disable this for a second. Right, let me do some materials here. So I'm gonna do a material library. Let's go inside. Let's create a Karma material builder. This would be my rock. And let's duplicate that one, and this would be my ground. All right, let's assign those materials. And let's pick the ground and assign the ground material. Let's create another entry here for the rock, and let's assign the rock material. All right, that's basically it. We need also some kind of lighting, so let's use the new Karma physical light. Why not? Let's use some Karma render settings. Let's select here our render camera. Whoops, there you go, and set this one to something like HD. We're gonna be using CPU because I'm still not happy with what XPU does. Also, this is quite a heavy thing in terms of memories. I'm not sure if I'm gonna be able to fit everything into my CPU. Also, let's go to image output, actually advanced, and I'm gonna set this one to path trace. Let's do something like 32 or something for now, samples. Cool. All right. Let me take a look here and see how things look so far. All right, that's good. I don't want this to bother me, so I'm gonna set the specular to 1 in terms of roughness, just for now. Okay, let me check if my color correction is actually working. Yeah, so we're using sRGB and ACES. There you go. Okay, so the first thing that I see is that we need more exposure here. So let me disable these icons, okay? So we can control the sun and the light here, right? So let me use something like 2. All right. What's the color of these guys? 0.8. All right. So let me set this one to some kind of neutral gray, so we know better what we're doing. All right. And potentially we can go even higher in terms of exposure. Actually, let's see how this intensity thing looks like. Yeah, not that good. All right. So maybe 3, something like that. And I want to lower the sun a little bit. 30. 35. All right. And no, sorry, not that one, but this one. I want to get something backlit, kind of. Yeah, so maybe this is fine, but maybe we can lower it a little bit. Yeah, something like that, and we might even go to 4. Let's see, because then surface scattering is gonna do its thing, so it's probably we're probably gonna change this. I want to make these shadows a little bit longer. All right, let's do something like that, and 3.5, something like this. Okay, so this would be our base lighting. Okay, so far this is looking good. We need the displacement and everything for this rock, right? All right, I'm saving. That's what it's taking a little bit to refresh. Okay, so let's go to the rock and let me go here. I'm gonna bring back the roughness to, well, no, actually I don't have to do that because I'm gonna attach the image straight away. So let me go to Material X image. This is gonna be a float. And let me go to jobs, assets, and I need the roughness. There you go, that's my roughness. So specular roughness. All right, so that's the roughness of my rock. Let me duplicate this one and select the displacement. There you go. And let's connect this one to the displacement. All right, and I don't remember what was the offset that we used before. I think it was 0.8 or something like that, right? This is set to float, this is set to float. Let's use a subtract here and subtract 0.8, I believe it was. There you go. Okay, let's see. Oh. Okay, yeah, that looks good. We might need to subdivide this rock a little bit more, right? So let me go to my, let's do this. We can do it at any point, but I'm gonna do a geometry render geometry settings, right? So here we can select the rock and we can set the dicing to something a little bit better, right? Because if we set this one to 0.1, for example, we're gonna get less detail. If we set this one to, let's say, 3, we should get much more detail now in the displacement map. There you go. This might be a little bit overkilling. I'm gonna set it to 2. All right, this is not basing camera yet. To do that, we need to basically enable dicing by camera in the render settings, right? There is a geometry section here, and we can enable dicing based on camera, but you know, we have a static camera, so who cares? I think that is a little bit out of focus. That's because by default, Karma has these camera effects enabled. So I'm gonna disable depth of field. I don't want to use depth of field. I want to use motion blur though. So that's all good. That's looking good. What else are we missing? We're missing the albedo, right? So let me go here, duplicate this thing, select the albedo, and I'm gonna select this one to color. I might want to change this slightly, so I'm gonna use a color correct just in case, and I want to connect this one to the base color. And of course, this is a multiplier. No, that's all correct. Let's see how this looks. All right, cool. Yeah, it looks good to me. That looks like the rock with all the beautiful detail and everything. It's a pity that it's all going to be hidden by the snow, right? Everything is going to be covered by the snow, but all right, that looks good. Right, let me do one thing. I want to work a little bit on the material of the ground here, but you know that Karma behaves really bad when you have displacement. So I'm going to disable this displacement. So when I make changes, everything goes faster, and I'm going to enable it right after. Okay, let's see. All right, so let me go to the ground material, and here let's create an image, or actually a tiled image, and let me go to one of these materials that I have here, this snow thing. I'm gonna choose albedo. Let's see how this looks like. So I'm gonna connect this to the base color. Come on. All right, let's set the tiling to, do I have, I'm gonna use a triplanar projection instead. Okay, so let me use that, because I don't remember if I have UVs for my thing. I don't remember. Do I have UVs? I might have UVs. Otherwise, we can just create UVs. Yeah, I'm gonna use a triplanar anyway. All right, so I'll copy that over all the channels. And let's play a little bit with the size, right? So we need to use, we need to multiply these somehow, right? So let me do, let me see if I remember how to use these materials. It's been a while, but basically I think it's the position, right? So if we do a multiply and we take the position of that, right? Was it like this? I don't remember. No. Let me see if I can remember how to build this triplanar projection in Material X, because it's been a while since I did it last time. I think we had to do geometry property value. No, there was something, but I don't remember. I need to look it up. I completely forgot how to do the triplanar. All right, I just remembered, right? I actually recorded a video about this, but sorry, I don't really use Karma in production, so I forgot how to do it. But yeah, basically you just take a material X position, that's it. This is on object space, and then you have your material X multiply, and then you multiply the size. So I'm using something like this. I don't know what's the right scale. Yeah, maybe it's something like that. Let me duplicate all of these. Let me find and maybe the roughness now. Okay, let me connect this one to the specular roughness. We just want something very simple to cover the grid, right? The ground, because most of it is going to be covered by snow anyway. All right, and finally, well, this one should be set to float. And finally, I'm going to duplicate that one. And we need the displacement. So let's select the displacement. Great. Let me save the scene just in case. Displacements are a little bit complicated with Karma sometimes. Okay, it's saving up. Will be ready soon. So let's connect this one to the displacement and see what we get. Okay, I think everything jumped. Let me get rid of the color for a second so it's easier to see what's going on. So if we set this one to 0, yeah, it has jumped. So again, it's one of those mega scans things that we don't really know the midpoint or the neutral point. So I would assume it's 0.5. Okay, let's double check. 0. Yeah, that seems correct. So I'm gonna make these, I don't know, maybe like 2. Something like that. We might want to add more detail to that one as well. So maybe we can just duplicate that one, set these to maybe 1. We don't need that much definition there, and set the ground there. Okay, something like this. Let's pipe this guy again. Okay, great. And maybe we can make like bigger patches. So I'm gonna take these, I'm gonna copy parameters and paste relative references there and there. And now here I'm gonna copy parameters and paste relative references here and here. And now we only need to worry about this control. Let's see how that looks. All right, that looks better. Okay, so we get like a little bit more of the green stuff, which is supposed to be the terrain under the snow. Okay, great. I think we can basically go back to the rock and enable the displacement. So everything looks as expected now. Okay, good. That's all good. That's all as we want it to be. Okay, cool. Next, I'm going to take my grains. I'm going to ignore these two guys for a second. And now we need a material for the grains, right? Let me tell you, I'm not really happy with volume rendering in Karma. It's definitely way slower than the old Mantra volume shader. At least on all the tests that I've done. Again, I don't really use Mantra in production, so I don't have much data to compare. But back in the days, I used to use Mantra quite a lot for volume rendering, and it's definitely faster and actually looks better. So I don't know, maybe Material X shaders for volumetrics are not that good just yet. I don't know, but it looks definitely better with Mantra, and of course with Arnold, and it's also faster with Arnold and Mantra than Karma. All right, so let's use a Karma pyro material, or actually a smoke material, we can do this, right? Whoops, sorry. There you go. And this will give us kind of like the basics of it. So yeah, here we have everything we need basically. So let me call this one grains material. You can also go here and you can use like a karma volume material. And then you would have to connect a volume shader, but I would assume this is even slower. But anyway, I'm going to use this thing, the Karma Pyro shader, right? So let's pipe this here. Let's create another entry and let's take the grains here and my grains material. And let's start rendering this with a CPU. And that's what we get. So this doesn't look any good at all. Wait a second. Let me check. Yeah, no, that's all good. That's all good. All right. Let me go back to CPU. So first of all, the smoke color, right? That should be closer to 1, right? Because snow is extremely bright. It's the brightest thing in nature. All right, great. So here we have something. Should we go to a different frame, perhaps? All right, let's do something like this. Okay. Can we do like a rendered region of maybe here? Will that work? Yes. All right. So there are a couple of things that we're seeing here. Things are working, but it looks very thin. So let's multiply the scale by something like 15. There you go. And that looks better now. Is 15 too much? 10? 10, 15, something like that. We want to see these harsh lines and everything, so hopefully that should be fine. Let's see if we can grab like a bigger... I think this is a good area. All right, yeah, that looks good. So that's one thing. Shadow density, I mean, we should see some light coming through, right? So I'm gonna set the shadow density quite low to something like 0.25. There you go. So it's a little bit, looks a little bit translucent that way. That looks pretty good. We don't really want to change much here. We could enable scattering here and do some stuff here, but this is actually using attributes that we don't have. So this is not gonna do much really. What we can do, I mean, and this is powdery snow, right? So something that we don't have with a volume shader is code or specular, right? So if you go here, there is not really a way of controlling the specular. We have anisotropy, but it's not the same thing, right? We could build that on top, but we would have to create some extra attributes. Maybe I can show you that in another time. But I'm not doing like wet snow here. It's more like very fresh snow, so it has this kind of powdery look. So I think this just looks fine, right? To me, this just looks fine. What else? Another thing that we can do that I haven't done in my renders because it takes way longer to render. And again, Karma is not very fast. I haven't done it here. But you can add scattering in the rendering, right? Because right now we don't have any depth in the scattering, meaning that the light is not really coming through, but we did this cheat, right? This shadow density to 0.25. So it kind of looks like it, but it's not really doing it. So we could go, I just pressed saved. So it's taking a while to save. Okay. So we could just go to the render settings. We could go to limits and the SSS limit, the volume limit is set to 0. So if I set this one to 2, you see like this is now much brighter, right? I'm gonna set it to 1. This is now much brighter, meaning that we probably need to tweak the lighting. But this is gonna take way longer to render, and Karma is not super fast, and to clean all this noise in the volume, it might take hours. So actually, this, I'm gonna set that one to 2, right? And again, if you don't think this is enough, you can probably, and by that I mean like the lighting is not coming through enough, you can just, keep working with the shadow density and you might achieve something similar. But yeah, I'm not happy with how Karma behaves with scattering, with volume scattering. So I'm not really going to wait for 5 hours a frame for this thing. Okay, but this looks pretty decent to me. The good thing is, look at all the beautiful constraints and chunks that we built. Now that is all showing up in the simulation, so that's pretty cool. All right, let me move to another frame, perhaps. Motion blur is working, and yeah, everything is working. So we don't really need to bother too much. I mean, you can see that all the nice clumping and all the nice variations are working fine. Again, this is quite thick. The emission source that we use for the grains is quite thick, so of course it's going to cover the rock quite a lot, right? But yeah, I mean, things are working very well. Again, these should be perhaps a little bit brighter, because snow is really bright. It depends on the time of day and everything, of course. So I don't know. To increase the brightness, again, you increase the volume limits, and that will make everything brighter. Or you can just keep it like that to be more efficient and faster. And perhaps you want to, I don't know, increase a little bit even more the brightness here, so we get something really bright, right? This might be just too much. Oops, that's not enough. Yeah, something like that. Okay, let me do one thing. Let me enable everything. So I'm gonna get these 2 guys back, and let me just render. I'm just gonna do a render region because I don't want to wait for everything here. But this is basically the same lighting setup and everything that I did. I mean, I think in my render, I did a little bit more contrast, as you can see here. But aside from that, that's pretty much it. So yeah, I have more dense shadows than here, but here now you can see the rock and everything. Let's do a render region there. Yeah, but I mean, it looks pretty cool, right? It looks very nice. But yeah, I mean, volume rendering is always very slow, right? It doesn't really matter what render you use. It's always going to be slow. It's probably the most expensive things to render these days. But yeah, again, I don't have very good experiences rendering volumes with Karma. It doesn't look as good as other renders, and it's definitely slower. But yeah, play with it. Maybe render a bunch of variations using tops. You know that I have a tutorial about tops, so you can create multiple variations overnight and then go to sleep, and next day you would have multiple renders. But generally speaking, I think it looks good, right? It looks pretty decent to me. So again, I'm not going to waste any time here. By the end of the render, it will look like something like this. The only thing that I did again is just to render with better sampling, not to get that much noise. And I tweaked a little bit the contrast in Nuke, and that was it, right? As you can see, it looks a little bit, it looks quite cool. It looks a little bit underexposed to my taste. I mean, the snow should definitely be brighter. So I think in this render that we're doing here is gonna look better, right? And then we do a little bit of contrast and color correction in Nuke, and it will look better than this render. I think this is a little bit underexposed when it comes to the snow. You can see that my ground is actually brighter. So this would be probably the right color for the snow, but I was too lazy to fix it after I rendered it. But you can do that. I mean, here it's probably still a little bit underexposed, I would say. But of course, you don't want to have any clipping or issues like that. But yeah, I mean, look at all the beautiful detail here, right? All of that looks very nice to me. And I think this is a pretty effective way of creating this type of props for environments. Again, at the end of the day, you don't need to cache the whole thing. Here we're rendering like 120 frames. So, just select the last frame of the simulation of the rasterization, get rid of everything else, and then you would have a single file that is not that big on disk. And now that you have the setup, you can reuse this with many different assets, run everything through TOPS network, and overnight you can create 10 different variations, and next day you would have 10 different props that you can use. And of course you can optimize them, because if you're not this close, you don't need this crazy simulation or this crazy resolution. You can basically maybe you don't even have to use the point replicate to get 10 times the amount of points. You can just use something lighter, so it renders faster. But yeah, for close-ups, I think this would be a good approach. Okay, so let me know what you think, if you think this is a good approach to create this type of assets. Again, this might be a little bit overkilling for environments, but I don't know. I think it will create something very nice. It would be very cool to see if one of you guys make a scene, like a complex environment, using this technique for foreground elements. Of course, this is for foreground elements, right? Don't use this for background elements, because it wouldn't make sense.